All right, so let's get started. Welcome everyone to the fifth version of the LatinX in Computer Vision workshop. So we're all super excited today to be here. Thank you all for those who came today very early to attend the workshop. And thank you all to our speakers. I see some of them are here already. Yeah, so let's get started. I hope you enjoy the workshop. Some pro tips, let's start with them. I think a lot of people is asking for the Wi-Fi. You just get here, just got here, you don't know how to access Wi-Fi. Ideally, you won't be accessing Wi-Fi during the workshop. You will be attending the talks. But yeah, so the network is CVPR 2023, and then the password is going to be Vancouver. That's the way to access the Wi-Fi. Yeah, so this is going to be I hope you are going to be staying during the entire conference. So I hope you enjoy the conference here in Vancouver. There are a lot of things to see in Vancouver, so enjoy the conference as well. Enjoy beyond the conference as well, not only the conference, but try to explore the city and so on. Yeah, so let's get started by acknowledging LatinX in AI, which is a non-profit organization which actually creates opportunities for LatinX in different fields of AI. There are multiple activities like volunteer-led activities. There are opportunities for career growth. There's mentoring activities. So I really encourage you to look at the LatinX website and explore all the opportunities it offers to the community. I think this is a great opportunity for all of us to network and create a community. So I just really encourage you to check it out. Probably most of you have already know about it. That's why you're here, but still even if you have friends or people in your network that doesn't know about LatinX and AI, just share with them all these opportunities. Yeah, so I think one important aspect of LatinX and AI is this forum and members. So there's this LXAI app which you can access in your phone or through the web, where you can actually talk with other people in the community, share job opportunities, also collaboration opportunities. So I, again, encourage you to get there. I think it's been a pleasure working with LatinX in AI because I see how fruitful it is. And one of the nicest things I think about LatinX in AI is this opportunity to giving grants to students to attend conferences. I think this is a unique opportunity. I always tell this, every time I come to a conference, this is probably 10, I've been attending CVPR for around 10 years already. And since 2 years, I've seen more Latinx people coming to the conference. And I see this is something unique that just started happening 2 years ago when we started doing this, or Gilberto and others, and Laura started doing this Latinx in computer vision workshop. I see more Latinx people in CVPR, which was very rare. I remember always we used to sit in a single table or 2 tables when we were having lunch during CVPR, only 10 different people coming from Latin America. But now we have maybe 100 people coming from Latin American communities. And yeah, so by the numbers, you can tell that LatinX has sponsored a lot of this travel. It's more than 1,000 travel grant applications so far. And this CVPR alone, I think we sponsor around 15 or 20 people for coming to CVPR and attend CVPR and present their work. So thank you, LatinX and AI, for giving all these grants and allowing people to attend these conferences. Yeah, so this is not only CVPR, goes beyond CVPR. There's also sponsorship for other conferences like NACOL, ICML, NeurIPS, and NVIDIA GTC. These are some testimonials, just one snapshot picture, but I know for sure, if this is the second time you attend this Latinx in AI workshop at CVPR, probably you have the experience. This is a very unique opportunity for all of you, right? So this is one testimonial, but I know for sure at the end of this conference, you will have your own testimonial, right? So I think that's what matters. And yeah, just reminder, if you haven't joined it, just join the Latinx in AI community, the website. Yeah, I think that would be super helpful for all of you. This is just a reminder that we are just 1 day away from Juneteenth, and this is Day of Freedom, and I just encourage you to just maybe check out if there are any activities related to that in the city and celebrate the Day of Freedom. Okay, so let's wrap up like this intro session by giving thanks to all the organizers. Like, I really like to acknowledge Carlos and Stefania, who were co-organizers, like who actually deal with a lot of the organizational logistics of the workshop. Also to Karen, Gilberto, and Victor, who actually help us like with the outreach, like communicating with the broader CVPR community about the event and making it like a popular event as it is as today. It goes beyond that. So there's also chairs who actually took care about like the program chairs, like dealing with all the papers, posters, and like chasing reviewers, organizing all the program committees. So thank you, Alejandro, Paola, and Tatiana. I see Tatiana is here. So thank you, Tatiana. And a big thanks for Rodolfo and Daniel. I think they actually took care of all the presentation details. So yeah, so they took care of everything. So now it's not only a physical conference, but there's also a virtual element of it. So there's a lot of complexity in organizing all the presentations. So thank you, Daniel and Rodolfo. And thank you to our sponsor chairs, so Amanda, Lydia, and Karen. So thank you all for your help on like trying to find resources for the workshop. And this actually helps a lot for bringing people to the event. So that's a great work. And thank you all to Lourdes, Johnny, Martin, Francisco is here, and Lacey is here. So thank you all for your contributions to the workshop and to the organization. We also need to thank our sponsors. I think they are a key element of the workshop because we need resources to bring people to the conference. So thank you, Google Research. Thank you, Meta. Thank you, Amazon. And thank you, DeepMind, Adobe, and Apple, who sponsor the workshop in different forms. And with that, maybe let's have a sneak peek about the program. I think now we go to the exciting part. So in the morning, we will have two stellar speakers. So we have Henry, and then we will have Nina. And Henry is going to be talking about optics. That's a big high-level summary, but you will hear from him what he's going to be talking about. And Nina is going to be talking about context in computer vision. And in the afternoon, we also will have another keynote speaker, Miguel, who is going to be talking about generative modeling. And then we're going to have an exciting tutorial, remote tutorial from Luis Serrano. He's a very popular influencer in YouTube. Like, he's a content creator in YouTube. And he's going to be talking about how these image generation models work. So he's going to be doing an in-depth tutorial about image generation. And with that, this is a snapshot of today's agenda. So if it is too small, you can actually go to the latinxinai.org/CVPR2023, and then you can check out in detail the program in there. With that, I would like to thank you all for coming, but I hope you enjoyed the workshop today. And with that, we're going to have our first keynote speaker. I believe Karen is going to introduce him.
Well, hello again, everyone. I am happy to introduce our first keynote speaker in this morning. I present you to Henry Arguello, who received a PhD in electrical and computer engineering from the University of Delaware in USA in 2013. Since 2006, he has been a full professor of the Department of System Engineering and Informatics at the Universidad Industrial de Santander in Colombia, where is he the leader of the high-dimensional signal processing research group. He was named a senior member of IEEE in 2017 and was a visiting researcher at Stanford University in 2020. He has published more than 100 papers in international scientific research journals and holds 3 patents right now, His research interests include high-dimensional signal processing, computational imaging, optical imaging, compressed sensing, seismic imaging, medical imaging, hyperspectral imaging, and deep optical sensors design. So welcome, Professor Henry Arguello. Thank you for coming today to the LXAI workshop in CV.
Do you listen me well in the back?
Carlos.
Thank you, Karen, for the introduction, for the nice introduction. And my name is Henry Arguello from Universidad Industrial de Santander. And I am the leader of this group. This is my web page, and this is my email if you want to contact me. I live in a small city in Bucaramanga that is 30-minute flight city from Bogota. And I work in this lab in optics. And I'm going to present today this talk, privacy via deep optical coding for computer vision tasks. Before I start the technical part, I'm going to show you my history. As I mentioned, I study in Colombia, and after I moved to US to complete my PhD. And when I finish, I need to take a decision. I need to remain in US or go to Europe to get a position. But I have this idea to come back to Colombia and try to create a big group with this international impact. I come back to my country and I try to create this group, but this is the reality when you go to Latin America. You don't have any budget, you don't have maybe students, but with some effort, after some years, I received this budget or this, for example, this lab, and it was very good. But the introduction is about how I get this, how I start to grow in this way. When I start, I don't have, as I mentioned, any grants, but my government started to give me some budget, and after some enterprises in Colombia, and also the government, and after US also start to create in this group. And that was very good because I have this budget in Colombia that this is very good to make a good research. And the same for the students. I start with a few students, but after the group start to increase the number of members, but a lot. And that was very good because I have now 50 students, postdocs, and I can make a real research similar to US or Europe. And the areas that I work was several: computer science, electrical engineering, physics, mathematics, etc. But I mentioned you how I can do this in Latin America, especially in a small city. And that city is not Bogota. Maybe Bob, you know Bogota. It's Bucaramanga. That it's very far away from the, from the capital. And I developed this equation. I am sorry. Can you help? I developed this equation here, and this is the percentage that I put to the local research, and this is of course the percentage that I put the international. And if I put lambda, for example, if I put lambda to 0, that means that all the research is international. And that is going to, this is very good because maybe I can publish very good articles, international articles, but the problem is the funding, that when you put the lambda to 0, the impact in the regions is very low, and that is going to create to you a problem. And also, the another possibility is to put lambda to 1. This is very good because now you get a lot of funding from the government, but maybe you don't like that you are doing because it is very local, the impact is very local, and you only work in a local problem. And for me, I try to calculate what is the optimal value for lambda. And in my case, this value works very well, 0.4. I mean, 40% of the region is totally local and 60% is international. And that works very good for me. But you see here in this picture, I have another problem because I have this local part and I have this international part. And you have here a separation. And I understand that I need another term. I need to regularize the solution, okay? And I create this term, this additional term, that is, maybe you don't see, but it's the correlation between the local and the international. And that is very nice because now I have together the two words, the local and the international. Let me explain. For example, if I work in agriculture in Colombia, I work in a very local agriculture, as you see here. This is me, okay? And this is, I work also in spectral imaging with the, for example, with the Navy in US. And all the technology that I develop in international, I try to apply that locally. And that works very well because I receive funding from the two parts, from the government and also international. I need to mention that you need an equation for everything. For example, for the collaboration, you need also equation. I mean, you have local collaboration and you have international collaboration. In my case, unfortunately, this is the number that works for me. 10% of the collaborators are local and 90% are international. And that works very well. When I start, I collaborate principally with Europe, but after I start to make the same with Latin America and after the US and Canada, and that works very well. Now the network is very big and the group is very stable internationally. Also, that happened with the students. I need a value, a lambda value for the students. I mean, 40% of the students remain in the country and 60% of the students go abroad. I mean, when they finish the PhD program, they start to work in other countries. They move to another places, but as I mentioned, I keep 40% of the students in my country to continue with this idea. Finally, in this introduction, I just want to mention that maybe this equation can work for you. And really, I apply the formula. When I apply for funding, 40% of the idea need to have impact locally and 60% international. Okay. After this, I'm going to move to the technical part. Okay, I'm going to move to optics, and let me start with this deep optical coding design. When you need to capture a signal, and you need to capture information, for example, high dimensional information. Here you have the space, the angle, the time, the wavelength, and the polarization. You have a limitation because you have just a two-dimensional sensor. That is the principal limitation because you want to capture all the variables at the same time. And as you know, this sensor integrates the variable, and now you have a problem because you want to capture all this information at once, but you cannot. What is the one solution? To codify the signal using these optics, these coding elements. And here you have the input, you have your coding element, and you capture this projection. And after that you have this projection, you apply some computational algorithm, and you recover the underlying signal. That is the simple idea, okay? This coding element can be this coded aperture, this grating, for example, these polarizers. You can use, for example, deformable mirrors. You can use diffraction also. This technology can be used for whatever, or for example, when you codify directly the sensor. I don't know if the people here is from optics, but let me explain very easily what is the effect of a lens. This is a normal lens. You have a PSF, and if you modify the lens and you create a very complicated lens, you are going to distort the PSF, okay? And this is the effect that you have in the sensor. If this is the first PSF and this is the second, okay? When you modify the lens, you are going to have this kind of blurring in your image, okay? And my presentation is about this kind of lenses. This technology can be used, for example, for light field, can be used for spectral imaging, for polarization. And the idea, sorry, these coding elements, as you see here, can be random structures. I mean, you don't design anything, or you can design properly the structure of these elements. That is the idea. In the picture, you can observe the impact of design or non-design these elements. You see that the quality here is better than this. If you decide to design the coding elements, you have two possibilities again. You can design the coding elements without data and using data. When the design is without data, this is very nice because you don't depend on the data, and you try to minimize this kind of functions. And when you have a database, you try to minimize this. Okay, but the solution is different. Of course, the database-based solution is very good. As you see here, this is the database solution. It's very nice, but you know that this depends on the database, of course. And this is the solution without any data, and this is the random solution. But what is the procedure to design these optics? Normally, you have a database and you have a task. And you have an optical element that you want to design. And you start with some decoder that normally is a deep network. And now you convert the optical element, you model the optical element as a layers of a network. And after you train all these, and after you convert again the layers to the optical element. That is what happened. Okay. And now you have your optimal design of your optical elements. And normally you have some fidelity term that is related with the task, and some constraint that is related with the physics of the optical element. And I apply these principles to, for example, to spectral imaging, as you see here. And this is the optimization, and this is without any optimization. I apply this also for light field, as I mentioned before, and also for spectral imaging, sorry, and also I apply this for depth estimation. Give me a second. And also I apply this for depth estimation. I design a lens to with one snapshot try to calculate the depth of the input. And but my presentation is not about projection, it's about privacy. Okay, I'm going to move now. I'm going to move now to privacy. And I have this idea that if you observe the measurements, the projections, they look like very blurry. They look like that maybe the people don't see really what happened in the input. I mean, this picture and this picture, they are are maybe different, and maybe you can use these optics to protect the information from the input. That is very good because we move from the projections to the privacy. And now I can use this technology of compressive spectral imaging, compressive depth to privacy. Let me explain better the idea. When you capture a signal, okay, maybe the hardware part is very nice because it's something secure, it's very nice. But after you discretize the signal, when you put this information in a computer, you have a problem because somebody can access the information, okay? And you have some operator, for example, the people that maybe store the information, and that person can send the image to another people, and you have a real problem here. And you have this problem, for example, in medical imaging, because you are maybe naked, and you know for security reasons you need to store all the operation, and you are totally naked, and somebody is seeing the information. For example, the people that is operating the computer, not the doctor. It's the people that operate the information. And that person can send the information to another person, and this is some method. And now you have the same problem in surveillance, you have the same problem in sport, etc. And also, normally, you after you discretize the signal, you apply some, as all the people here apply some computational algorithm to do something, to do some task. For example, pose estimation, I don't know, action recognition, whatever. But in all these parts, the information is unsecure. Maybe the hardware part is nice because maybe it's difficult to hack the hardware part, but this part is very easy to hack. Okay, and there is a solution for that problem in the software part. You can apply some post-processing, and you can protect the information using this kind of solution. For example, you can compress the information, you can do some pick selection, do some blurring, but that solution are in software. I mean, somebody again can access the information before you apply the algorithm, and that is again a problem. And my proposition is a little different. I'm going to protect the information from here, okay, from the sensing part. And this presentation is about that, how you design a lens, okay? This is that this person is going to see, you see, totally blurred, totally protect the information. But you need to complete the task, but you cannot reconstruct. I mean, with this measurement, you cannot reconstruct it. It's impossible, but maybe you can complete the task, maybe the pose estimation, action recognition from this projection. And this is the idea, how you design this optical element to protect the information, but you need to complete a computer vision task. As I mentioned before, you have this scheme, you have the database, and you have your task. And now you have a fidelity term that is related with your task, and now you have this term that is related with the private part. I mean, you need that this image and this image, they need to be totally different because the information need to be protected. Of course, you have a value here, a lambda value, and that value is extremely important because it's the balance between the task and the private part. And let me show you the effect of this variable, the lambda. If the lambda is small, of course, you don't protect the information. If you increase the lambda value, you start to protect the information. But if you increase so much the lambda value, now you are good because the task is maybe is good. This is the ground truth, and this is the task using this information. But if you increase the value more, let me a second. maybe you are going to see anything, but also the problem is that the task is not very well. The performance is not that you wait, because this is the ground truth and this is that you are obtaining. Okay, this value is very important, and you need to decide how much do you want to protect the information. Okay, I'm going to show you 3 examples. The first is pose estimation using this technology, action recognition, and also theme captioning. This is a very nice application. The first is pose estimation. You know, this is computer vision. You know, this application. I don't need to explain to you this. And for the training part, we have, this is the, as I mentioned, this is the cost function. This is the fidelity term, and this is the private term. Okay, we want to this term need to be maximized. This term need to be sorry, this need to be maximized, so this need to be minimized. I mean, this image, these 2 images need to be different. And this term is, look at this. This is the input, and this is the measurements. They need to be equal. It's going to be minimized. It needs to be equal, but in the important points. I mean, in these points, that is very important for you because they are related with the pose estimation. And we train all these. We train all these, and we convert to the lens, and after this is that we obtain. This is the traditional camera. Okay, this is a normal camera. You know about this, but you are going to see what happened in our camera. This is our camera. You see, totally protected and the same. It's the same. You can obtain the same pose estimation. You can see here. It's very nice application. Now, also in action recognition, you have the same. You have some actions that you want to recognize. And here we apply a little different approach. This is the database that you have. This is the actions. And this is a little different. This network is already trained. And this network tries to attack the measurement. I mean, this network tries to discover something. For example, this network tries to detect a face, or try to detect the color of the skin, the gender. They try to detect something in the measurement. Okay, and you have again this cost function, the fidelity term that is sorry, the private term that is related with this attack. I mean, you try to minimize the probability that this network discovers something. That is the idea. And also, of course, you try to do this image totally different. Okay, and the fidelity term is divided in 2. The task, this is the task that is related with the action, but also you have this term that is related maybe with you have a videos in action recognition. You have a videos, and this term is related with these 2 images. You see, this is the previous layer before the last one. Okay, this is the features of the previous layer to the last one, and this is the layer when you use your database, and this is the layer when you use the secure information. Okay, and you try to regularize. You try to do these 2 matrices of these 2 features equals. That is the important part in the regularization. Okay, and this is that you obtain. This is that you see in a real camera, in a normal camera, sorry, and this is our camera. You see anything, and this is the action. They fail. Sometimes they fail. Sometimes it changes, and the system fails. But the probability of fail is very low, and the information is totally protected. Okay. This is the last one, the scene captioning. This is very nice. You are going to see. And this is, you have an image, and you want to describe the image with these captions. Very simple. But we want to do the same, but private. I mean, we want to calculate the description of the image, but we're using a private signal. The same, we develop this algorithm and calculate the length. We have the fidelity term, the private term. The private term is the same. And now you have this term that is related with the captioning. Okay, this is related with the caption, and this is related, with, of course, with this transformer, because you have correlation between the information, and this is our task fidelity term. Okay, we design the lens, and this is that you obtain. This is a normal camera. Okay, and this is some examples. I don't know what is here, but this is the description, and you are saying here a dog is standing next to the red bike. Maybe you don't see a dog here, but maybe you can see here. This is the ground truth. Okay, and this is our solution, and this is that the user see. You see anything? You don't see anything really, but you have maybe a good description of your input. Okay. This is an example of the real implementation of this system that we created in our group. And in the last part, I'm going to move to another application. Okay, that is an extension of this of the security part. That is the authenticity. Authenticity is also important. It's a little different, because you don't want to distort the image, but you want to know if the image is if anybody modified the signal. For example, if this person have access to the information, this image can be distorted. I mean, you can do. You can manipulate this image, and you can distort the image, you can hack the signal, and this is a real problem. And also maybe you want to know if the image is or somebody modified the information. That is the problem here. Okay, and if as I tell you, this information can be modified, as you see here. Somebody can modify the signal very easily, or this guy can send the information to another person and modify the information. Of course, you have a software solution. The software solution is to encrypt the signal or apply a key in the image. You apply some software key, and if somebody modify the image, you are going to know, because you have some encryption in the image. Okay. I'm going to mention again that this problem is different because you don't want to distort the image. This image needs to be equal, almost equal, but you want to apply some key information, okay, in the pixels of the image. And this is, okay, sorry. And this is our solution. You see, we are going to design a lens that apply some codes that you don't going to notice. I mean, this image and this image is going to be equals, almost equals, but if you apply some network, you are going to discover that inside of the image is you are going to see this kind of patterns, and you are going, if you modify the signal, you modify the image, and after you apply this network, you are going to know that somebody modified the information. And this is very nice because the key is in optics, not in software. Okay, and now all the information is secure. That is the idea. Again, we apply this end-to-end scheme. We have your fidelity term that is related with this is related with the task, and this is related with that you want that these two images need to be almost equal. Okay, and this is the procedure to train the system. You have a database. The database is generated by some generator as the GAN, and you generate a database, and you have your real image, and you have your key, you have your this optic element, you have your optical element. You protect the key using subnetwork. You have these features, and now you have your databases and your protected key. You train this system to discover if the key was modified. That is the idea. Okay. And after you train the system using this cost function, this is the fidelity term related that you want to know that these two images need to be equal. This is also the same, okay? And this term is related with the key. The network try to discover if somebody modified the key. That is, but with some example, you are going to understand me all this, okay? Let me show you one example. This is the original image. This is when you put a key, the hardware key, you see the images are almost equal, okay? And this is the original key. And this is the key that you calculate from this image, okay? And you see they are almost equal. But if you modify in some way the image, the input image, for example, this in the mode, this is the effect in the key. I mean, it's a lot. You modify just the mode of this person, and this is what happened in the key. You see, you can know that somebody modified the signal. Okay. Maybe you said this is very easy because I can see that somebody modified the signal, but you don't have the ground truth. Remember that. I mean, you don't know if this is the real image or this is the real image. Okay, but using this technology, you know that the information was manipulated. Also, that happened in this example. You see, this is the original. This is the image that was protected, and this is the manipulated image. You see the effect in the key. Okay. Okay. With that, I conclude my presentation. I was to remember you that we moved from coded projection to privacy. And also that you can apply this technology to different tasks. I know that another group, for example, in youth, is working in protect the deaf information because they developed some lenses similar to this. And also, this is a problem that we need to solve, the balance between the reconstruction and the private part. To calculate this parameter is very difficult. Normally, you calculate that parameter using trial and error. That is the solution. Okay. I'm going to remember you my email. If you want to visit my group, we are very happy to receive in Colombia if you want. Normally, we have several visitors in this group. Okay. Thank you very much for. Do you have any questions?
Hi, thank you for the presentation. I had a question on detecting several perturbations on this type of changing in the images, because you show an image of a face that I think is a very obvious change in images. But what happens with a perturbation that is too small? How to be this method for detecting perturbations?
Yeah, I don't have here, but you mean the sensibility here?
Yeah.
That maybe you change just a pixel?
Yeah, maybe a very small part of the image that change the classification of a hormone.
Yeah, we are working in theoretical, try to establish the difference between the manipulation in the real space and in the key space. But I don't have the the distance. But we know that in the training part, we try to maximize the difference in the key space is going to be bigger. But this is the problem that we are working now with some students.
Can I ask based on that? So I can see that we want to make sure that if there's a strong manipulation, we can identify this. But what if there are some changes like compression, something that, it's not a malicious attack. It's just you need to compress the image, you need to rotate it a bit, you need to crop it. How would you, how would this handle this? Or make sure that we still know that this is real, but compressed.
Ah, okay. No, yeah. This is a good point. Thank you. This is a good point, but at this point, if you compress or you rotate the signal, you are going to distort the key. But I can include that in the optimization. I mean, I can include that the rotation needs to be flexible to the rotation to the compress, but I need to include that term in the optimization. I mean, in here maybe I need to include this as a regularization term that maybe it's the same the image in position than another position, but this is also a possibility. Yes. Thank you.
Thanks.
How did you produce the results for the post estimation comparison? Because I understand that your method is related to the acquisition of the pictures.
Yeah.
So if you use a data set, an existing data set, how do you modify the pictures from the existing data set?
I mean, the simulation part.
Yeah,
Because we have a video, we have the optical, the optical mathematical model of the optics.
yeah, but in the example there is an existing data set in the people
Yeah.
dancing.
Yeah.
I don't remember the name of the data set. But,
Yeah.
did you post process the images? Or-
Yeah. I mean, apply because this is a video.
Yeah.
We apply the distortion of the optics, but digitally,
Okay.
electronically,
Mhm.
and after we apply our algorithm. Yeah, but this is just simulation, but in that case it's simulation.
Yeah.
But we have also a real and it's because it's comparison. I need to use a video.
Yeah, but
compare.
how can you be sure that the post processing that you apply to the system data set is
Yeah.
equal to the effect that is producing the physical artifact in the camera?
Yeah, no, we don't know. No, we don't know because you have reason. I mean, it's approximation of the effect of the camera.
Okay.
Yes, you have reason. But in the real test.
Yeah, I mean,
was-
you cannot find the data set, your
Yeah.
own data set, you apply with that, but that makes sense, but in the comparison, it doesn't make sense.
But we have comparison with real data. I mean, we the camera, okay, you have here something.
Yeah.
I mean, it's difficult because you need to produce the same, the same video. It's very difficult.
Yeah.
But I mentioned, maybe the person can try to imitate the same performance, and that is the solution that we have.
Okay, thank you.
Yeah, maybe, yeah, thanks for the presentation. So one question about the privacy preserving action recognition, like, the word that you presented, like, I wonder what's the limit, right? Like, are we gonna be able to recognize all possible actions, like if we have these compressed, because somehow it's some sort of like compressed representation of like actions and the video itself, right? So where do you think is gonna be the limit? So what kind of actions are gonna be out of the scope for this type of technology?
Yeah, for now, if you see the presentation, the actions are very general. I mean, they are, in my opinion, it's very easy because they are just, you move the mouse, you are making exercise, they are very general. But if you asking me for a specific task, I mean, that is related with a patch of the image, not the entire image, it's going to be very difficult for the network. For example, that something happened in some percentage of the image, maybe 10% of the image, but if you see the actions, they are very general. They the percentage of the image related with the action is maybe 60%. It's a lot. And for that reason, it's easier to detect the action.
Maybe post-related actions should be easy, but like hand-manipulated things may be hard. Like if you are manipulating something with the hand, like cutting like
Yeah.
tomato versus cutting onions.
Actually,
Like
the
slicing.
pose is the more difficult
Oh.
because the pose has a details in the pixel. But if you see the mouth, it's just to say you open the mouth.
Hmm.
I mean, it's easier that you said the details about the pose. That is the more difficult application that we have.
So thank you for the presentation. I really like that you started with the human side, so like building a research group in Latin America, like that.
Yeah.
Not easy, of course. So my question is more like, from the human side, how do you actually build, let's say, your collaboration outside of Latin America, for example? Because I'm in the opposite side. I work in Europe. I also want to build collaboration with Latin America. So maybe you can tell us about that.
Yes, I don't know if it's correct that I explained the history, but when I started to create the group, the people from Europe go to Colombia to try to help me, to help the Latin Americans because you don't know anything. That is my problem because and they are scared because it's Colombia and we have some security problems. But when they arrive to Colombia and see the lab and see the students, they are very nice and very wonderful students, they say, man, what are you doing here? This is Iceland, and you do the same as me. And some guy go to there, and after he explained to another person, and after another person want to go to Colombia to see the experiment that I am doing, that is making research in Latin America, but with the international impact. And after that, the people start to go a lot to my city, and that was very good. And after I moved to US, and some people from US also go to the lab. Normally, I prefer that the people visit me because the impact is bigger than if I visit Europe or US. And but when I start was difficult, I don't criticize the Europeans because I understand. I mean, they don't believe that maybe they are doing real experiments. But after that, they say, okay, this is the same. I mean, we can start to collaborate, and that was very good. And I received the same from different groups because that person explained to another person. For example, in France, they have a very good network, and when you convince somebody, they explain to another person, and now they have opened the possibility to collaborate with a lot of people. But that was very good. And if you are happy to, if you want to visit my lab, that is very good because I only in our group we only not present maybe the technical part, but also the culture, because we don't have a real experience to show the culture. I mean, when I go to France, I know that you are going to drink a good wine. For example, I go to Bordeaux and I know that it is wine. But when you go to Bucaramanga, you don't know what you are going to do. And that maybe that is very good because we eat ants. You don't know that, but and they are very good, and people don't know that. And even me don't. For me, it's very strange that I don't give ants to the people. Normally, I go to a nice restaurant and buy a wine and give that to the French people, and that is not the correct way. Maybe I need to show the real culture of my city. And after that, also the collaboration starts to increase because they want to discover the place. Okay. And it's a nice history because the ants is just $5, and the Bordeaux is maybe 200 euros. It's very nice because when I go to Europe, I receive a Bordeaux, and when they come to here, they receive ants. Sorry, in the back.
Yeah. Thank you for the presentation and congratulations for your wonderful lab. I have a question regarding to the data privacy with the hardware. Is there any common feature between the different optimized lenses for different tasks? And can you have a single lens or several lenses for multiple tasks at the same time?
Yeah, it's a good question. No, normally we decide that you are saying I can use the same lens for different tasks. I mean, for pose, for actual recognition.
Orientation is similar.
Yeah. No, they are very different. They are very different. I just showed you lenses, but really that is not a good the optimal solution. You can use a more complicated technology. For example, diffraction, diffractive elements, but the problem is that they are very expensive in Latin America. Maybe in US, you can print or you can fabricate a diffractive element for, I don't know, $100. But in my country, this is maybe $3,000, $10,000 to print an element. But the answer to your question is no. In this case, you need to train the system for the task. And they are totally different.
Thank you. First of all, congratulations on your work. It's really super. I find it really, really interesting. I have a couple of questions. The first one is, I mean, once you have the design of things, like what the lens, similar to what we were answering, the earlier question. Do you have a comparison? I mean, because if you have the, let's call it the digital design of the lens, and you have this kind of key, and you want to apply that onto the digital image that was previously applied with something that is not the on lens. Do you have any data of how that would compare, particularly with the security one, with the detecting fakes? Do you have any comparisons of how that applying digital the filter would compare against acquiring the image with the filter itself?
Yeah, that's a good question. Normally, you can do no. Physically, it's impossible to do the same digital than physically. Why? Because you have to rely. I mean, you have polarization, you have spectrum, and you can modify whatever in the sensor. But after you integrate the information in the RGB detector, you can only make a combination of the pixels. Okay. But before the integration, you can do whatever. You can modify the color in another way. You can modify the polarization of the information. You can modify the depth. You can modify whatever that you want. You can put a key in the depth. You can put a key in the spectral in the. But you cannot do the same when you have an image, three image. Okay, it's impossible. But I'm not saying that the software is better than the hardware. I don't know because the question is what is better, the software solution or the hardware solution?
Not quite. I mean, because I understand that your solution is hard.
Yeah.
And I understand that, and it's fantastic. I'm just saying if it can be like, if having a model like this could be used to be applied for already digital image.
No.
Because that would be amazing.
Yeah, I understand but the question. Yeah, you have this. No, but no, it's not possible. It's not possible. No. Because this is more secure because because it's the physics part. Yeah.
Of course, yeah, I understand, and I understand that's not in research. I'm just thinking if that could be like extrapolate.
Yeah, extrapolate. Yeah.
It's amazing. Also, another question I was wondering, like this kind of adversarial attacks. I mean, I see that because that could be applied also on digital image. That's not the problem that we're solving, right? So also that like changing one pixel in the image, how relevant that is? Because I also see that changing one pixel in the image is not noticeable. Usually, but for the problem of deep fakes and all this stuff, I don't think it's relevant. Like changing one pixel, because in the end of the day, with one pixel, you are not going to produce an image that can be used negatively to certain real issues. Like I understand changing a pixel if you're doing a classifier and you have an autonomous vehicle that doesn't detect a stop sign, stop as a green light. That's what but in this case,
a good answer to the question that somebody it's a better answer than mine. If you modify a pixel, maybe it doesn't matter.
Yeah, I would say that
it doesn't matter.
The researcher,
but the question that somebody did is what is the distance between the modification in the real image and the distance in the key space? And this is a very nice way of research to maximize the distance. This is our optimization, like to maximize the sample peptide. But you are saying if you modify a pixel, I mean the difference is going to be not between the two technologies.
The most interesting part of the talk, actually, we have to go.
Yeah.
Thank you very much.
Yeah. Thank you. Sí. Okay. Okay. Thank you. Okay, now I am going to present the three speakers, oral speakers for this session, which is Joshua Rubio, William Costa, and Roman Jacome. Just as a reminder, we have 7 minutes for each of your presentations, and at the end, we are going to have a question and answering session. Please, Joshua.
Yes, so at the end, I will go place, so stay here.
Yeah, then stay there. Yeah, I see the bigger guys stay here, so they can take the questions from there.
At the end of the three presentations, we are going to take questions. And please try.
So can you hear me from here? Yeah. So good morning. I'm Joshua Rubio. I'm part of the team of researchers at Samsung Tijuana. We collaborate a lot with Samsung America, and this is part of our collaboration. I'm one of the authors. Marco Contreras is the other author. I'm going to present to you wildlife image generation from SINGRAPH, which was a work that we did last year, and we want to present this at this workshop. So text to image generation, as you know, has messy attention. There's a lot of work on this, mainly through diffusion models. This interest has exploded in the last 2 years, mainly to DALL-E, ChatGPT, Midjourney. Each time that a new tool is released, this explodes on the internet. So you can see the trend from 2018 to 2022, it exploded on whenever DALL-E and Midjourney was released. So there, as I mentioned, there's a lot of work on diffusion models. There's a lot of work right now on CVPR, and there's a lot of work on Archip each day. And it produces highly quality images, but sometimes it doesn't work as well with limited data, or maybe if you have very strict deadlines to tackle an issue, it's not going to be the perfect solution. So for this kind of environments at Samsung Tijuana and SRA, we work with a solution to try to generate these realistic images with good proportion between the objects on this challenging environment. So this is a same parametric approach. It's a tailored approach for some of the issues that we have at the company. The idea is, of course, use text input, and at the end have this synthetic image. We tested it with the wildlife scenario because this was a POC. We didn't develop a full solution. We want to focus on these wildlife scenarios for one of the projects that we have at the company. So the proposal is very simplistic. As I mentioned, we use a semi-parametric approach. The idea is to get SINGRAPHs, in this case, encode information from text to this plane, then create masks for those and retrieve images from an image bank. The main issue with some of the approaches that were developed in 2018, 2019 are the issue between the scale of the objects. So we tackle that with linear regression. Then we use a hyper network trained to remove any bigger artifacts on the background. And then we use canvas composition for those, and one of the parts of SIMS networks to try to blend the images with the background and remove any smaller artifacts between the objects and also the backgrounds, and do some color balance, which was very nice because we then knew that the network was capable to do it. So for the first part, the idea is to get the information from the text, encode that to SINGRAPH, which are relations between objects and edges, and then create these C layouts. The network that we work based on is called LG2IM. The issue with this is that end-to-end solution from 2018. The issue is that the upper part of this didn't generate good quality images. So the idea was to get only the masks. As I mentioned, we get the text, encode this information to SINGRAPH, pass them through graph convolutional layers, and then through an MLP, which then is creating this object embedding, which then are passed through an object layer generator. The idea is to get an average of the information from the mask embedding, and then use the box relation network to get an idea on the initial size and also on the position of the objects. Then we blend those to generate the initial coarse scene layer. But several experiments, we detected that the relation between the objects was very good, but the final masks were not as good. So very simplistic idea was to get those masks from the bank of shapes to get an initial detail layout. So what we did then was to retrieve those masks and use them as a reference for the background and also for the scale images. We use a Curie dataset for this, and we pass the retrieve background, which will have some issues with bigger artifacts, which are then removed with a high field network. that was trained, as I mentioned, with forest information and also other nature scenarios. Then we got the objects, which are then scaled to the relationship between the different objects. In this case, an elephant on the same perspective should be always bigger than a sheep, unless they are on different perspectives. And then we use canvas composition for this. For the object, we use boundary relations whenever we do the canvas composition to apply the SIMS network, which help us to do color balance whenever we try to blend the objects with the background, because sometimes the objects have different color temperature than the background, and that's what's messy for us. And also to get the remotion from any of the smaller articles for this. So as I mentioned, it was a very short POC for us. We worked on this around 6 to 7 months. We use a Coco as a base reference. We got around 20,000 images for this. We trained MSG, which is the shorter version of AG2AM, and we took around 4,000 images to very fast train as the SIMS network, and Open Images Basics to get the animal data bank. We created experiments to do quality and quantitative comparisons. Quality comparison was done with manually graded SIGGRAPH, and quality comparison was done with randomly generated SIGGRAPH. So here are some of the examples that we got with the manual SIGGRAPH. So as you can see on the images, with the data set that we used to compare, on this case, we didn't compare exactly with any fusion models at the time. That was done later, but not included on the paper. Our results have higher quality, higher risk quality, although with the addition of some objects such as tree, the realism is lost. It works better with general backgrounds. And we did some experiments by fusing MSG with SIMS, and the quality was better also with our work. And here are some of the quality results that we have. For all the metrics, with the exception of the inception score, our output was better. We think that the inception score was not as good as the one that we had, because even though the images were not realistic, they were more similar in the hyperspace composition than the images that we were using. So that might be the issue, but the difference is not as big. So here are some of the results that we have with one animal. So for these purposes of the company, the images were good at that sense. We did some images of 64 by 64, and some other our original resolution of 640 by 480. So we didn't plan to do any of these on higher resolution than any of these, because it was a POC, as I mentioned. And here are some of the examples using higher count animals. The model performs well under most of the conditions. The biggest issue was with birds, because the birds that we obtained were not as good as we expected. So that was the main issue for this project. So as I mentioned, this was one of the things that we collaborated with Samsung Research America, and that's all from my side. Thank you.
Yeah, thank you, Yoshio, for the presentation. Yeah, you come. Julian. Yeah.
So please let me know when you start.
Yeah, you can.
Okay. Hello, everyone. My name is Will, and today I will present a method for high-level context representation for emotion recognition in images. I did this work together with Stefania Talavera, Lucas Figueiredo, and Veronica Tyreb. So we all know that emotion recognition is something that is required for us as humans to develop skills. So when we are talking or interacting with someone, we are looking at the faces, the body language, we are seeing the facial expressions, and this helps us to understand and then connect with other people. So these signals, these emotional signals, we receive them and we can decode this naturally, meaning that I know that a face that is smiling, this person is kind of happy, for example. However, many emotional states are not communicated explicitly through speech. So I know that you never went out with your friends and everyone's laughing and saying, haha, I'm so happy, or I'm so neutral. Because these are actually some things that are communicated non-verbally. So we see the faces, we see the body language, and this is how we understand each other. So this information, we call this non-verbal cues because we do not explicitly say them, but we express this to other people. And besides the common non-verbal cues, such as facial expression and body language, we also have context, the situational context, meaning that the context in which you are placed is going to be interfering with your emotions. So for example, if we were now watching an horror movie, then we would all probably be fear, right? So we would be having fear of the movie. So we also take into account the stimuli of the environment to understand the emotion of others. But why? Why should we then understand the emotions of others? We know that recognizing human behavior could allow for a deeper understanding of users, but users of systems, apps, but also citizens in smart environments, citizens using smart spaces. And then when we can comprehend each one individually, then we can now act to impact the perception of those spaces. An example of this is, imagine that in a park, a lot of people are feeling happy, but then they all change their emotions to fear. Then maybe something is going on at the park and you can call the police or call security service, for example. So we hypothesize that generating high-level descriptions could be more assertive to unseen data. So we are not looking at one park, but multiple parks. We're not looking at one room, but multiple rooms. And then when we deploy this to solve real-world problems, then this model would be able to work well in this new unseen scenario. And also, in some scenarios, these high-level descriptions are sufficient. So, for example, in a public park, I do not need to look at each individual person and see their emotions, but rather having an overview and then work towards it to make a decision, or then a city planner could work on top of this. So our proposal is to generate these high-level contextual representations of emotion, and then use this to act, to make decisions, and then to have the overview of the emotion in that scene. So our method is, given an image as input, we use ExpansionNet to generate a caption of this image, and we start working on top of this image to generate a new processed caption. So we remove, for example, stop words, we remove gender-related words, and we also add lemmatization to the words. So walking there would be just walk, surfboard would be surfboard, and then now we have our processed caption. What we do now is we store this information in a large matrix that in the future we will extract information from. And then with the all processed caption, we start to adding augmentation and adding semantic and scientific representations. So for example, if I say to you the word beach, what comes to your mind? So maybe something that is more peaceful, right? A white sand, sun. And we do this using CVPR. That is a large database of scientific representation. And the query from CVPR from beach is ocean beach, waterfront, ocean, coast, and sea. And we also extract from CVPR two scientific representations that are interest and elimination. And we continue building on top of that. So for each word here, we also query CVPR to extract a second level. So again, this is just for brevity, but in the overall scene, we do this for each possible word here in the image. And as you can see, this is starting to look like a graph, right? So we treat this as a graph, we start creating connections, we start linking these words, and then the weights of each node is extracted from this matrix that we have discussed previously. So for example, the weight between the valid words is the probability of the next word happening, given that we have the current word. So we start by adding these nodes, we start by adding emotions. So in our data set, we have 26 emotions, but here I show only peace for brevity. And at the end, we have a model, we have a significant graph, and we use evaluation of the gene model to make the classification of the category, and also a continuous prediction on the VAD model. So we experiment on the well-known emotic data set to train and validate, and we use the mean average precision, or MAP metric, to compare with the state of the art. And although our result is not the state of the art, we can see that it is close, and that the state of the art actually uses 5 nonverbal cues, while we only use 1 nonverbal cue. This means that we could take a word and we could plug and play each one of these other words, and then this would also lead to improved result. And notice that for each of nonverbal cue, you need to have a new model, a new encoding stream, and this takes time, this takes computational time. So the idea is that by having only one encoding queue, only one model, we are able to run this very fast in almost 100 frames per second on a consumer grade notebook. So as for our results, we can see again from that first image that the ground truth would be affection, and then affection was not predicted here because we are not looking at a person, so the model can't know that there is affection happening here, but we have anticipation, confidence, engagement, excitement, happiness, peace, and pleasure. So this is a very nice result from our technique. I'm just going to this last one because it's also very interesting. When we look at the background, when we look at the context, we can see a forest. So this again gives us a prediction of peace, disconnection, so you are far away from the city, but we are not looking at the person. And because we're not looking at the person, we actually get this wrong because the ground truth here would be fatigue, but we are looking at the overall information of the scene, and then we have the prediction there. So to summarize, we propose a method that looks at the context, starts adding syntactic and semantic representation to context, and it's fast, so it's able easily to be deployed anywhere. That's it. Thank you for your attention. Yeah.
Okay. Can you hear me? What? Okay. So hi everyone. My name is Roman. I'm today going to present the work that we did in our University of Santander, and with my collaborators Emmanuel Martinez, Alejandro Hernandez, and with Professor Henry. So in this talk, we are going to deal with the spectral images. The spectral images are spectral images have like valuable information across some spatial and the spectral domain of one scene, which is useful for classifying materials. So, could you click? So one of the problems dealing with
No. Okay.
one problem with dealing with the spectral images is that the instruments to acquire them is very expensive and requires long time acquisition. So when we want to acquire like several data sets of this kind of data, we are very limited by this expensiveness of the acquisition. And nowadays we are using deep learning methods for several inverse problems using spectral images, such as decoding with incompressive spectral imaging, mapping for RGB to spectral images, or performing high super resolution spectral images. So the state-of-the-art data sets are very limited compared with RGB images, which limits the performance of the computational task we are going to do. So how can we overcome this one? Is a very traditional solution, which is data augmentation, but data augmentation such as geometric transformation, flipping, rotation, and translation induces like few variances that are easily learned by the network and can like improve very good the performance. So nowadays we can use generative models that aims to find the distribution of our data set and try to sample new examples. And these are very nice. So we're going to focus on the traditional generative adversarial networks for this approach of the lack of data in spectral images. However, when we deal with spectral images, we have at the problem of the high dimensionality of data, because we have a high spatial resolution, a high spectral resolution, so we have a very large data cube. So this is difficult for the GANs to convert to something good. So with the problem, how we're going to tackle this problem is basically that we can represent our spectral images in a low dimensional space that preserve the most important information of this kind of data. So our proposed method employs first an autoencoder that aims to find a low dimensional representation of the data set. So we have here this low dimensional space of our data. And with this kind of low dimensional representation, we're going to train our generative model, but instead of trying to generate synthetic spectral image, we're going to generate synthetic low dimensional representation of the synthetic data. So the discrimination is only performed
with the generated low dimensional and with the low dimensional representation that we already learned from the original data set. So again, since we are constraining our problem to lower dimension, we are going to have some problems to have very good generation. So we propose also some regularization in the training of both the autoencoder and the generative model. And this regularization is focused on the variance of pairs in the autoencoder on the low-dimensional representation. So we compute some the variance because we have a batch of low-dimensional representation, and we compute the variance along the batch. So we compute how we changing these values pixel-wise. So we are going to have first, we are going to propose to minimize the bias to have a compact representation that helps later to train our generative model. But the effect for the GAN is that we want to increase the bias. So we put this minus sign here to increase this bias to have very diverse synthetic low-dimensional representation, and this helps us to have very good synthetic samples. So finally, when we train everything, we train our generator, we train our decoder, and we can have some random input, have a synthetic low-dimensional representation, and obtain the synthetic spectral image from the training decoder. So basically, this is how we create our generated data set. And I'm going to show you some of the experiments we had. We trained with this data set that have 1,000 spectral images, and we set this how we can compress the data in the autoencoder, but we already compressed in the channels in the spectral bands. So we vary from one channel to 16, having vectors for 1 for 3, and this is the one that we perform later for our experiments. So these are some examples compared with different channels and with the regularizers that you can see here. We have very different kind of latent representations with this by maximizing this variance of this data. And this is when you try to optimize using the full spectral image. So they can convert this to like nothing, a mess. So we can have now more sense to generate them with these low-dimensional representations. And we tried this for several inverse problems, such as a recovery from compressive spectral images. So we are going to these other two tasks. But first, you can see here that we compare using the baseline, that is like the original data set, using the traditional geometric data augmentation and with geometric data augmentation. So you can see here that with our proposal, we are having a very good a better performance compared with the traditional geometric data augmentation, and also with the GAN, it doesn't using the low-dimensional representation. So we have here the examples for how changes the performance when we add more samples, when we have more synthetic data, and we have better performance, of course, with channels equal to 3, and we have better performance with only using a GAN network in this case. Some reconstructions of the tasks we are completing, validating again that training our model training with the augmentation we propose are better. And finally, some remarks here. We propose a method to generate synthetic spectral images from low-dimensional representation of the data, which helps to improve the training of the GANs. And also a note that maybe we can extend this idea to different to new state-of-the-art generative models. So thank you. Is the code for our.
Okay, now, if anyone has any question for the three of our oral speakers. Yes, please. Yeah, yes, over there. Okay. At the back, the one on the right.
For a second invention. So
You were mentioning that you were like trying to remove all these kind of like gender bias things, to recognize this kind of like activities. But there are some issues, like for example, it was well known that, for example, when you were trying to translate, I think the doctor from English to Spanish or something like a gender language, actually was translated as the male doctor. When we were translated in nurse, it was translated as a female nurse, So I was wondering, like, if you're using, now that you're using English for that kind of like, if probably if you're using actually remove the gender bias in those images, or probably you can somehow mitigate that gender bias. Yeah, recognition. I don't know if my question was clear.
Thank you for your question. So in the data set that we use, that is emotive. It's the data set for emotional cognition. So we have the image and the classification for each image. These data sets are usually not very balanced among gender. So this is why I wanted to remove, because I don't want the model to look at the person and kind of create correlations to gender A, emotion B, and the C, emotion B, for example. So this is why I remove, because I want the model to be able to look at the scene and not look for cues related to gender that were assumed from the data set, but rather to look at people individually without considering gender and see how people are feeling. So this is why I remove the gender-related words, and also I remove boy, girl, and other related words so that it's not able to create genes correlation. So I don't want the model to create correlation. So this is why I remove them.
Were you able to observe actually? I mean, quantitatively, were you able to observe like that your model was not gender biased?
So no, I did not have this experimentation because in this data set we have one proportion, but in other data set we have a very different proportions. So this would be, I could assume that this would happen eventually if I let this continue in the data set, right? So there is another data set that the difference here is like 80 to 20% of gender difference. So yeah, I just wanted to remove them because it was clear that from the data set it would learn these representations. I did not have the experimentation to actually validate it, but looking at the data, then it would not have any other possible way. This would be the easier way for them, right? So yeah, I removed it.
All right, thank you.
No problem. Thank you.
Yes, please, on the back.
Do you have problems with the overfitting or using for the low props? Problems with
Sorry, is this question also for William? Thanks.
Okay.
do you have problems with low props or overfitting like this?
Yes, so we had some problems with underfitting at the start, but we did a hyperparameter search using weights and biases. So we separated the validation set from emotive, and then we started working on this. So this is why I concluded with that model that I showed here. So a variation of the gene model worked best for this because gene also has these unopened, right? So I don't know if you remember, but I had 5 levels of hidden representation. So these were able to actually generate very good internal representation. So this is how I solved it under fitting. In the paper, I compared my gene with other a simple thing that was the first method that was trying, which is a common graph convolution neural network, and then the difference was like 10 and 80. So I started doing this search using weighting biases, and then I arrived at the G model. So yeah, I had underfitting, but it was solved. Thanks for the question.
Is there one question more for any of other 2 speakers? No, if that's not the case, then we can go to the break.
Yeah, we guys have 10:40?
Yes.
Yeah, 10:40, so we get time to get.
Sorry, guys, we're just quick changing the computer. So we are going to move the section for like 7 minutes. Yeah, like everything is going to be like moved 7 minutes, so we can move all the time. Yeah.
Dile si cuando ya terminado, normal, porque puede tomar más tiempo.
Sí. ¿Tenemos las presentaciones en algún lado? Lo voy a copiar. No, ¿hay algún drive o algo?
No, yo creo que no USB.
Así que yo no tengo USB. Ah, bueno, estás. No, estoy lo
Y hay una carpeta en un folder.
¿Cómo lo mandaste?
Y adentro de mi folder está la
Pero luego le mandé
presentación.
como PDF porque me dijeron que no tenía PowerPoint, no sé qué.
Ahorita vemos.
Si tú puedes presentar un PowerPoint.
Sí, tengo un PowerPoint. Sí, pues sí lo. ¿Está en la carpeta? ¿Dónde están los archivos?
Está en su
¿El PowerPoint? Let me put yours here. Listo en las archivos. En la memoria. La presentación de María. Vamos a hacerlo con el full screen. View full screen. Darle compartir en Zoom. Le share. Está viendo el lector, ¿sale? ¿Dónde te dejo esta barra? ¿Abajo?
Si quieres, creo que hay una forma de esconderlo. Sí. Ay, creo que-
Yeah, so we are going to from now.
Estamos-
So we're going to achieve the schedule, starting from now. Yeah. Okay.
Yes. So welcome again to the second oral session of our workshop. So as I said before, we are going to start with Matías Valdenegro. So welcome, you can start. Remember, the presenters have 7 minutes to present, and at the end, we are going to have a question and answer slot. Okay, so please keep your questions for the end.
Perfect, thank you. So first, let me thank the organizing committee to organizing this wonderful event. So let me tell you a story about how we actually had this research made. So I am the last author here, and it's a collaboration with Octavio, Sebastián, and myself. So Octavio is from Mexico, Sebastián is from Colombia, and I am from Chile, but we are all working in Europe, and we actually all met in Europe while working in different places, mostly in Bremen. So Octavio had this idea about what happens if you look at the loss during your model training for each sample separately. And he theorized that this actually was related to the difficulty of a sample. And we developed this idea into this paper. So we present a method that evaluates the difficulty and biases of a machine learning model, which I think is a very, very important topic. You don't need to modify the model. You don't need labels for this. You only need to have a loss function. And we tested it in multiple computer vision datasets and tasks. So let me go directly to the results to show you the idea. You take a look at this. So these are samples from Cypher 10 for the airplane class. And what we want to do is find a score that tells you, is this sample easy, difficult, or very, very difficult, or medium. So you see all of these planes here are, you can see all of these are the easiest samples, these are the hard samples, and these are 3 different models. So these models kind of agree what kind of samples are difficult. These are all airplanes that are basically in the sky, like flying or on the ground. And all of them, you can see that they're very, very similar, but these are airplanes that are basically in the ground, or they are different airplanes, like these are civilian airplanes mostly. These are military airplanes or airplanes in like strange poses. So the model is telling you during training, okay, this sample is actually much more difficult to classify than the rest. And this is very easy to see in this figure. And also you look at the nearest neighbors of the feature embedding learned by the model, you can see that in the hardest samples, for example, this one, I think is a cat, the nearest neighbors are like a sheep, or so the model does not classify this correctly. While in the easy samples, like for example, this is a kind of, I think it's an owl. So also, yeah, it's also right, but sorry, it's also wrong, but you see that there at least makes more sense visually. So you can see that the model, of course, has some biases as any other model. So the intuition of this is that you look at the loss curve for each sample, and each of these has a different behavior. So what we do in this experiment here, again, inside FR10, I train a model and visualize the loss curve for each sample separately. And we do k-means clustering, and we set 3 clusters. And here you see, okay, this is the mean of the cluster, like the solid line, and the others are the samples from the cluster. So you see that let's say the shape of the loss curves actually tells you something about difficulty. So we said, okay, the red ones that decrease very quickly during epochs, these are easy samples. The ones that are kind of constant or decrease slowly are medium difficulty samples, and the ones that actually increase during training, which is what's actually surprising, because you usually want the loss to decrease, but that doesn't mean that all the elements or all the samples in your dataset will actually have decreasing loss. Some of them have increasing loss. And we said these are the hardest samples. So these examples, like the hard samples, are difficult to classify, or they're more likely to be misclassified. The medium examples, yeah, so. And the easy examples, the model classifies incorrectly almost always. So this, of course, relates to model uncertainty and other important concepts. So how do we define difficulty? It's basically the total amount of effort that you need to solve a task. And we define this effort as the accumulated loss over a period of time. So you go back to this. So we say, how do we actually quantify that okay, this is the shape of the curve that is easy, this is medium, and this is hard. We take the area under the score. So basically you accumulate the loss for each sample during training, and you use this as a score. So the scores that you see here are actually this accumulation of the loss during training for each sample. So for example, this airplane in total during the whole training process across epochs had 0.03 loss, which is very small. While the hard samples usually accumulate a lot of loss. That means that the loss is actually not decreasing, but maybe increasing even, or even constant. So you get kind of a constant or increasing area under the curve. Please. Okay. Now, this is very nice because you can do it with any model that has a loss. You can even use a loss that is different than is actually training the model. You can do it in the validation set, in the training set, and so on. So we also have like more computer vision results. Like this is results using the single shell multiple loss detector on Pascal VOC. But in object detection, you usually have multiple loss functions. You have the localization loss, classification loss, and objectness loss. If you look at the localization loss, this tells you what is difficult to localize an object visually, or especially in the. So you see the hardest examples on the top, and for example, it's a boat, and the boat is very tiny there. There's a train that is also very tiny, and the concept is very, very bad. There's a car here that is also very, very small. So all of these examples are very difficult to classify, especially this bottle, because here not all the bottles are actually labeled. And the model is confused, which is the bottle that you're actually predicting as bonding points. And here you see the easy samples for, let's say, localization. So it's where the is very big in the image, it's very easy to localize. So this is also a different kind of bias in the model. And finally, you can also see the per pixel score for semantic segmentation. So instead of getting a single score, you can also get a per pixel score, which tells you, okay, in this image, which parts of the image are actually difficult to classify and which ones are not. So for example, if you look at this image, so this is an image from, let's say, cityscape, I think. For example, all the road is basically difficult to classify, and only the static objects are basically easy to classify. And that makes sense because things are moving, so it's very difficult to classify them. And we also have some other correlations that we found. For example, you can also use them for curriculum learning, use the action score for that, because you try to say label the easy samples, that gives you much more information than the hard samples. And this, if you compare it to the random baseline, this is actually much faster to actually converge, but not by much. And I think also we had another result later that mentioned that how the action score relates to the entropy of an ensemble, which is a method for uncertainty quantification. It measures something that is different, but actually the uncertainty of the model. So thank you. And we have here the source code. So this is basically just a callback that we add to the model, and then you can capture all of this information. And of course, the idea of this workshop that, of course, after this, we will all be better. Thank you. I'm open for questions in the session later.
Ese archivo en PowerPoint, si podemos poner en PowerPoint. Sí, lo podemos abrir en PowerPoint.
Thanks, Matías.
Se llama igual que el PDF, eso presentación en PowerPoint.
Okay, and now welcome to David. Yes, all right.
Hey, hi, my name is David. My work is, our work is isolated sign language recognition based on three structured skeleton images. This is a work that I did along with the support of my advisors. So what is a sign language? Well, a sign language, as you could see, involves hand, body, and face gestures. And right now, it is estimated that there are around more than 200 different sign languages, and more than 70 million deaf people use sign languages across the world. And what is isolated sign language recognition? Well, it is the task of identifying the sign gesture that is being performed by a user within a video. And it is called isolated because it is the video contains a single sign gesture. Why is this important? Well, because very recently it has gained a lot of attention because isolated sign language recognition can enable developing educational platforms so that people can learn sign language in front of a computer when sign language classes are not available because of tight schedules, money, or a limited number of sign language teachers. But what is the problem? Some models have been proposed, such as pre-convolutional networks, to solve this task. However, these networks usually use a large number of parameters. That's why researchers have moved to explore skeleton-based features because skeleton-based features are less complex to process. And we propose to process these skeleton-based features using a method called tree structured skeleton images, which is a previous work that we take as inspiration. And as an overview of our method, we take a video and then we estimate the skeleton pose of the person. Then with the skeleton sequence, we convert that skeleton sequence into an image, and then we classify that image with a dense convolutional network. So we are basically converting a video classification task into an image classification task, which is less complex. This process is carried out by placing the joints in the column dimension and the temporal evolution of the joints in the row dimension. And this is done, the order of the joints in the column dimension is given by a path that is extracted by generating a graph representation of the skeleton, then traversing that skeleton graph representation, we depth first search. Then the joints in the order they were visited are used as the order in the column dimension. This ensures that the convolutional operations are carried out over neighboring joints. This means spatially related information. And we evaluated our model using two diverse data sets with, they are not lab control. It is an American sign language dataset and a Turkish sign language dataset. In addition, we also use a Mexican sign language dataset published by the work of Mejia Press. our results have shown that our model is able to achieve 1% more accuracy than the state of the art, while using only 64% less parameters. With this is a table of results with respect to the American Sign Language dataset. With respect to the Turkish dataset, we were not able to surpass the state of the art. However, we achieved 3% less accuracy while using more than 70% less parameters, which is very important for mobile platforms, for example. This is a quick demo of our model. This is me, and I am performing the two signs, corn and bird. And this model was deployed into a website. It is important to note that our model is doing the classification on the client side. It is not on the server side, which means that the information of the user is not sent into the internet. This avoids privacy issue. So as conclusions, our work represents an alternative for isolated language recognition while using a low number of parameters. As future work, we can explore other backbones besides LensTech and other mechanisms such as attention mechanisms. Well, thank you for listening. Thank you.
Is that right?
Okay. Hello, my name is. Okay. Where's the pointer? Here. Hello, my name is Juan Luis Gonzalez. I just defended my PhD thesis at KAIST, which is the Korean Advanced Institute of Science and Technology. And I will present detailed preserving self-supervised monocular depth with self-supervised structural sharpening by Juan Luis, Chejo, Moon, and Munchur Kim. Depth estimation is a task of mapping pixels to depth or invariance depth values. You can have multiple view depth estimation, which is taking multiple views as input, and the one that we are taking care about in this work, which is the single view depth estimation. The second is much harder because we have to not only exploit the low-level vision cues, but also high-level vision cues like relative object size, relative object position, and occlusion. Furthermore, you can learn depth estimation in a self-supervised manner. That is, there is no depth ground truths available during training. And for this self-supervised depth estimation, you can have either self-supervised depth estimation from stereo images or from monocular videos. In the first one, you have synchronized left and right images, which are much, they give you a much easier task. And on the other hand, you have the self-supervised from monocular videos. In this case, we have independently moving objects as the frames are not, all the objects in the frame are not synchronized. So we have the temporal issue. In general, for both cases, we have most methods, they underperform for depth boundaries and highly homogeneous and reflective regions. In this work, we want to, well, the previous self-supervised depth estimation methods, they rely on photometric reconstruction errors between projected images. And these projected images are projected guided by the estimated depths and camera poses. They could be generated either by backward warping or forward warping, which is depending on how you project the images, if you project the current view to the next view or the next view into the current view. That's backward and forward. In general, all these previous self-supervised estimation methods, they fail in the way that the incorrect depths can minimize the photometric reconstruction errors. And this usually leads to the depth maps leaking into the background. As we can see in these examples, the depth maps are not sharp. They tend to leak into the background. But when we add our method, which we call self-supervised structural sharpening, or S4, we can recover these structural edges, as we will see next. First, it's important to understand the self-supervised baseline, which takes as input a single view and outputs some probability volumes, which can be used to do the forward warping. This forward warping will create synthetic views seen from the previous and the next camera frames, and this will be compared against the ground truth, previous and next camera frames. These loss functions have some tricks. For example, they incorporate masks that remove the occluded regions that are not visible in the input view and the target view. And they also remove the pixels from the objects that are moving independently. Yes. In our self-supervised, well, this is more information about the self-supervised baseline, which we adopt some previous method that incorporates a forward warping. That is, we take the input image and we project it into the previous or the next camera frames in a novel view synthesis manner. In our proposed method, we ask ourselves, can we transfer RGB structural details into depth maps? And doing this without any additional data or ground truths. And for this, we propose the self-supervised structural sharpening. In self-supervised structural sharpening, or S4, we want the network to learn some structural sharpening operation from RGB input images only, without any additional data sources. And we do this by letting the network learn some general sharpening operation from randomly distorted images into the structurally consistent and restored input images. And we do this in a blind manner. That is, the sharpening operation doesn't know about the distorted image input. It only knows about the clean image input, which we have as input for our depth estimation model. Then, once we learn this restoration operation, we apply it onto the estimated depth map to have the structurally sharpened estimated depth map with S4. So this is the overall architecture. First, we can see this is just the baseline. And then over the baseline, we add our novel method, the self-supervised structural sharpening. For self-supervised structural sharpening, we make the network estimate additional vertical and horizontal separable adaptive convolution kernel values, which will be the operation that will learn how to sharpen these depth maps. We also learn how to sharpen these depth maps by first applying some blind amounts of blur and noise into the input image to generate the noisy image input. That is then also convolved with the locally adaptive separable convolutions to get the restored image. So this restored image is then compared against the input image, which is the ground truth. So interestingly, in this case, we are not doing any de-blurring or denoising. We are just applying blur and noise into the input image and then estimating some kernels that can restore this distorted input image. But at the same time, the network never knows the amount of blur or noise. So in order for these kernels to work, they have to be some kind of general structural sharpening operation. And then we apply this structural sharpening operation into the estimated depth maps to get the sharpened depth map. And then we further apply some guidance into this depth map just to prevent any textures baking into the final depth map to get the guided sharpened depth map. And this guy, then we can use this guy to supervise our initial depth estimate. So this is like a closed loop. We learn this sharpening operation, and then we use this sharpened depth map to refine the original depth estimation. These are some examples. As I mentioned, we don't do de-blurring or denoising. We do unblurring and unnoising. From randomly distorted input images, we learn this general sharpening operation from which we can get sharpened sharpened input images. And as you can see, they don't have a high level of details, but they are structurally consistent. And that's what we are looking for our estimated depth maps. Okay. Okay, yeah. Well, this is a result of filtering our depth maps with the learned kernels. And as you can see, we can get a high level of details. Furthermore, we guide these step maps with estimated disparity maps so that we can prevent the texture baking into the background. And we have these loss functions, which is have the traditional loss function plus the S4 loss. The S4 loss incorporates some multi-scale L1 loss and perceptual loss to further refine the estimated depth maps. And this is some of our results. And in summary, we get the state of the art on the Kitty dataset without using any kind of segmentation mask or very heavy network. In summary, well, in conclusion, our network with S4 tries to close the gap between the previous state-of-the-art methods and the fully supervised methods for the self-supervised depth estimation task.
Okay, thanks to our presenters, and I would like to invite you here at the front for the question and answer session. So Matias, David, and Juan here. Maybe we can start. Is there any question for Matias? Okay.
Thank you for the presentation. So I have a question because you present a metric, and usually the metric, you have loss quantity model. This metric is accumulated of the index. So are you trying to modify your metrics in order to improve this consistency in the echo during the training of a metric? I try to change a little because I need to modify something of the law.
Well, the idea is not to modify the model, but to get more information on what the model is doing to internally. Because all models have biases, and there's also bias in the model and bias in the data. So you need to extract the information to, for example, say, okay, these are the samples that consistently need classified, so they're more difficult, and maybe you need to do something about that. And these samples are easy. So, for example, you capture a data set, you never know, for example, okay, I capture a bunch of data until you will spray that, okay, this will work with a neural network. But now you can actually find, okay, these are samples that are more difficult. Maybe I need to gather more samples for this class or for this, let's say, pose of theory, and the other images that are very easy, then you can just keep them that way. Right? That is to get more information, not to modify this.
Okay. I will first ask if there is at least one question per presenter. Okay. Is there any question for David? I think you were Pearson, yes.
Hi, thank you for the presentation. So I want to ask, why do you not focus just on the end when extracting the thought of your packet?
Yeah, so even when you speak, facial expressions and meaning, right? So imagine how much it will affect in a visual system of communication such as sign languages. So we want to develop robot models. We must to account for facial expressions. For example, some linguistics work have shown that in some sign languages, the facial expression can change the tense of a verb. And in other sign languages, the same movement of a hand in combination with a different facial expression can change the meaning of the entire word.
Okay, and is there some question for Juan? Okay, yes.
Yeah, so you're using like RGB. I'm interested in that part where you use like RGB cues for the estimation. But there are like some. This is the question: is there or there are any scenarios where that would be actually bad? You know, like probably it's not there. I don't know. Can't imagine one actually.
Yeah, there could be some cases where the textual information is so strong that ends up baking into the estimated depth map. So that's incorrect depth map, use the texture. So to prevent that, we incorporated some weights in our loss functions to weight less the faraway region and also weight more into the edges of the depth maps. So yeah, it can happen. Thank you. Thank you.
Okay, we have 5 more minutes for the questions, so you can say the name of the presenter. And I think Gilberto, you had a question?
Yeah, I wanted to know,
Matias?
if there is a way of, this can be used as a way of measuring how this, like a shift, this like distribution shift between data sets and something like that.
Yes, but the thing is that since you can only do it on the train or the validation set, you can measure shifts between these two, like basically comparing test scores, but not to do it in new samples.
Okay, thank you.
More questions? Yes? Okay.
So now you know how hard it's, I think maybe it's the first question to receive it. You use this information to give you weight, it's try to improve their performance, but also down percentage or down because the performance will improve.
Well, we don't do that, but you can do that using the focal loss, for example, because that's a very related concept. I use the loss to a power of something to actually weigh it, right? But we didn't do that so far. Yeah.
Thanks. More questions? Yes?
So for the why didn't you use another type of data set from Latin people, right? Because you use one from Mexico, but the other ones were from here, right? And American people.
Yeah, well, that's because there are no a lot of public data sets for Latin American sign languages. And that's why this is a big issue, and this is an important topic to talk about it in this, especially in this work, because we need more work on generating data sets for Latin American sign language.
Okay, more questions? No? Okay, yes.
Yeah, for the great work, and thank you for bringing me to this. I work in sign language and translate as well. It's a big issue. I have a couple of questions. One, have you tried your method in continuous sign language? And two, how do you deal with the uncertainty of the hallucination methods? Because usually there's a problem when estimating methods, and it's okay if they can explode, but if it's a little bit far, like in the real world, it's a little bit complicated to estimate the terms of how do you do that.
Yeah, so regarding to the first question, no, we haven't tested this model with continuous sign language recognition. Yeah, we know that this would be the next step because there are more applications for continuous sign language recognition. And regarding to the second question, well, to take in account the subject distance from the camera, we normalizes taking into account the size of the chest. And also we use that augmentation that simulates different body sizes. But yeah, it is important to know that post-estimation models can change the performance of a model. Yeah.
Okay, thank you so much for your attention in this oral session. And I think we can also clap in sign language according to one of the presentations. No? And thank you.
Yeah, thank you, everyone.
La tarde.
Pero lo que se lo pueden quitar ahora. Se lo pueden quitar.
Ahora viene
Venga.
la presento yo. Okay, now we continue with the next keynote. The keynote is Professor Nina Hidata. She's an associate professor at the Computer Science Department, Institute of Mathematics and Statistics at the University of Sao Paulo, Brazil. She has a long experience in teaching and research involving pattern recognition, machine and deep learning, computer vision, covering fundamental methods and application in the fields such as astronomy, oceanography, biomedicine, and document image analysis. She enthusiastically promotes education and scientific training on machine learning and artificial intelligence through student supervision, courses, and talks. So welcome, Professor.
Good morning, everyone. First of all, I would like to thank the organizers for the invitation. It's a great pleasure to be here. I'm very happy. Today, I will talk a little about context in computer vision. It's not about results, but I think kind of panorama. So I will go back in time. So something I would say is kind of old, but it's okay. So before, let me find here, okay. Before starting the presentation, I would like to talk a little bit about me. So I have a degree in computer science, PhD in computer science in 2000, so I'm not too young, okay. I work as a professor in the computer science department of the Institute of Mathematics and Statistics, University of São Paulo in São Paulo. And I'm in computer science because I have always liked math. So I actually went to the university to do math, but then I had the opportunity to take introduction to computation course, and I fell in love with computation, so I changed the course to computer science. And another thing is that I like to draw, so my interest was in some sense computer graphics. But since our department had no professors working computer graphics, I went to do my graduate studies in image processing and pattern recognition. And then from that, I am working with image processing, pattern recognition, and machine learning, computer vision. And today it's what I do. Okay, so for those that don't know, I think usually we don't know other countries' reality. So there is São Paulo, and where is the yellow pin is the capital of the state of São Paulo City, where I live. And São Paulo is in the southeast part of the Brazil. And okay, now some facts from the Universidade of São Paulo. I would like just to highlight the number of students we have. It's the largest university in South America, at least. We have almost 100,000 students, including undergrad and graduate students. And USP, Universidade de São Paulo, has 7 to 8 campuses across the state of São Paulo. And where is highlighted in the center is the main campus in São Paulo City, where I am working. Okay, so now a little about my background. I have been working initially with learning morphological image operators, which means given an input image and the output, an expected output image, try to learn which is the morphological operator that takes the input image to the output. So this was my work during my master and PhD. So a lot of pattern recognition, but basically mathematical morphology. I have been also working with interactive image segmentation. So this is just a screenshot of the tool we have developed. And the idea is that the user can mark the object and the system will segment the object, find the boundaries. Another thing that I have been working is handwriting recognition, and especially recognition of mathematical expressions. And this is a solution based on graph modeling and graph grammar, actually. And we did this for math expression and also for flowchart recognition. Other thing that I have been working, object detection. So this is QR code recognition. And here the idea was to recognize the 3 patterns on the corners and then do some geometrical analysis of the patterns to decide if it's a QR code or not. And this part of the research, I would say it's pre-deep learning era. So basically some key words to highlight my research would be mathematical morphology, graphs, and machine learning. And then we changed to deep learning. Many things changed. Now basically I'm working with deeper learning. And that is allowing me to work also with multidisciplinary problems like people from astronomy or oceanography, medical imaging, and so on. And I just want to highlight one work I'm doing right now, which is labeling data using projections. So suppose you have a lot of image, for instance, oceanography, you have some cameras underwater and they take images continuously and they want to recognize plankton. What we do is use some convolutional neural networks to extract the features from the objects we capture and then do projection, which you can see on the left side. And here you can see color on the projection because we know the class of each object, but in general, we wouldn't know the class, so you just would see the spread of the points, but you can see some clusters. And when you select a piece of this map, so if you look, we are selecting these images and they are shown there. So it is possible to quickly check if all the objects that are shown on the right side are of the same species, for instance. And you can maybe uncheck some that are not and label them quickly. So this is a very, I wouldn't say very efficient, but it's sure much more efficient than looking image by image. Okay, enough of background. Let's go to the topic I would like to talk today. So today I would like to say a little bit about context in computer vision. And as I said, I will go back to in time, okay? So first, before that, when we are talking about computer vision, there are some issues that have been problems in the past or are problems constantly, like semantic gap, variation of the images and the context. And I will cover this and get to the context actually, okay? So in the early days of computer vision, we had some image processing algorithms, and that's basically what we could do with our machines or data and so on. So things like thresholding, filtering, to do contrast enhancement, to detect the edges, binary segmentation, template matching, morphological filters. So examples like just remove noise from document images or detect some objects, very specific objects, template matching, were things we could do, detect edges. And these are very low level information. So that relates to what people use to call the semantic gap. So we could do this, but how to translate this low level information to the high level information. Okay, that was a problem. And then typically to solve problems, we had to build very complex pipelines. So here, just an example to segment and count cell sizes or something like that. You had to take the image, do some correction of the illumination, do thresholding to separate the objects of interest, then segment, take the measure, and so on. So a very complex task. And the problem is if you change your microscope or whatever, you had to do everything again. So very time demanding and very specific for each task, for each domain or each set of images. And regarding variation of the image, there are problems with poses, size, shapes, color, viewpoint, and so on. This is very well known by everybody. So these are the challenges in computer vision. And okay, now what all this has to do with context. I talked about the thresholding, for instance, which is point-wise processing. So there is no context in there thinking about the content of the image. You're just looking an isolated pixel and kind of doing the threshold. So this is a point-wise processing, no context at all. When we think about the filters or morphological operators, for instance, we just consider a small neighborhood to process a pixel. And to do tasks such as object recognition, which is more higher level, we need a more global context. So just to understand, if I show you these two images, could you say what are they? So without context, it could be 0, or maybe something else. But if I show this, you can say which is which, right? Well, at least in Brazil, we know that the first 3 are letters and the 4 last one are the digits. So we know that it's a capital O and 0, right? So context is very important to understand what's happening inside the image, right? And this picture is not mine, but I found it is very interesting. We can see, for instance, thinking about object detection, you start from pixels at the right, then you have some parts of the object, and in the middle you have the object itself. So you have the global view of the object, and for the to the left you have local context of the object plus the global context where the object is located. So this is not new, of course, and based on this kind of idea, many important methods have been developed in, I would say, in the early 2000s, basically. And that involved, for instance, development of a lot of handcrafted feature structures. Probably you have heard about safety, whatever, corner detectors and so on. And of course, also feature selection, once you have a lot of features, which of them are important for your task. And also part-based models in which you try to have a sense of spatial relationship between parts of the object, for instance. And another one bag of features, I will show an example right now. And of course, machine learning algorithms were very important to take advantage of the amount of features. Okay, this is just to show an example of using bag of features and getting the global information from the image. So I don't know if you are aware of this model. If is, I want to explain, but basically the idea is that you have classes of images for learning. You have a code book or a set of words, visual words, and you can extract these visual words from the image. And for each class, you will have a bag of visual words. So the problem here is to just train a classifier to recognize the object based on this bag of features. And recall that these features come from the entire image. So in some sense, you have the global context of the image. And for the recognition, you just do the same. You take the image, compute the words, you build the bag, and classify it. Okay. So then after some years, we have deep learning, which is a breakthrough, and I think the most important part is the fact that deep learning learns representation of the data that is more adequate for your task. And another characteristic is the fact that it's data-driven. To make it more clear, I think this is a very nice diagram, and it's not mine also, just to illustrate this evolution of machine learning in computer vision. So in the early days, what we had is that process of extracting features and then training classifiers and getting the result. Then first advance with deep learning was we could use convolutional neural networks, for instance, to do the feature extraction. So no more need to select features or extract features by hand. And now what we have actually is something that is completely free of feature extraction, so end-to-end processing, totally data-driven. Okay, and why this, how this has to do with context? As you know, when we deal with convolutional layers, as you stack layers, you have a larger and larger receptive field. So actually the decision taking at the output is taking into consideration a large portion of the input image. So obviously you are considering a large context. So that's why you can take advantage of the global information in deep learning. And also fact of you do resizing from one layer to another means that somehow you are taking into consideration multi-scale characteristics of the patterns or features that are being computed. And this, the whole process is end-to-end, and therefore it's very easy to handle in terms of just building a model. Okay, so now talking about context, so I would like to emphasize the question of data context, which means the context that is present in the data itself. And as I said, convolutional neural networks and vision transformers are able nowadays to take into consideration the global information of the image. But there are situations on where one image only doesn't contain the context or information I need to in order to get some information. For that, we can consider situations with, for example, multi-view images that will complete the information in some sense. And then we have some challenges here, which is how do you integrate this, for instance, these three views to extract the information about the environment that is being observed. Okay, so what is possible with deep learning nowadays is that we can integrate information from multiple modalities of data. So it could be multiple cameras taking the image from the same environment, or you can use audio and video together, or image with text description, for instance, and so on. And with vision transformer, we can do that, or people is doing that a lot nowadays. And an immediate consequence of all this is that we are able nowadays to extract higher level information from the image, something that was not possible like 20 years ago. It's completely impossible. And of course, semantic gap has been largely reduced nowadays. However, we have also problems due to the size of the network and so on. So we need a lot of data to train these models, large computing resource, memory processor, and so on. And interpretation is very hard because the network is like a black box. So, in terms of context, when we talk about the context image in computer vision, we are usually thinking about context in the data itself. But I think it's very important to us to consider context in terms of what we know about the problem we are trying to solve. So one important context or scope is prior knowledge about the information or the problem we are dealing with. So actually, we do this maybe not so consciously. So usually we work with a specific image domain that in some sense is shaping our context. We set some task that probably is set in some context also, in the sense that, for example, if you are solving classification problems, we have usually very well defined classes, right? Okay, but I think important context or information regarding, I mean, like prior knowledge would be things that could be useful in general problems, like physical models, hierarchical relationships, spectral information, which we find in many applications, many problems. And the question is, how do we include this kind of modeling in the learning process or in the learning model? Obviously, there are many works that do that, but in many situations it's very specific to a domain or a problem. But can we do that in a more general way to serve to many applications? So I think this is an important question. And so regarding context, I mentioned context present in data itself, and context external to data, which is prior knowledge. But I think when we think about computer vision problems, we need to think also about use condition related context. What I mean by that is we can develop a very large and robust model, but when where we are going to use that model? No, so in many cases, we need to deploy the solution into a edge device or hardware constrained situation. And therefore, we cannot afford to just build a large and big model, because how will you use that, right? And there is also security related restrictions, as mentioned by in the first talk. Explainability is another issue. So there are many issues, and what I think we need in computer vision now is to work this, or at least these three contextual scopes, they must be worked together. So in summary, I would say that we have some problems that involves computer vision. So we have these scopes, use condition, multi-source, multimodal data, and some prior knowledge about the problem. And then the information extraction process have to deal with a lot of issues to tackle these three contextual scopes simultaneously. And I think the challenge is in there. How do we find solutions that satisfy all the scopes we are considering? And at the right, we have some other issues related to after you have the model, how do you understand or how do you explain what's happening, right? And to conclude, I lost track of the time, sorry. So I will conclude. Okay, thank you. I will just conclude. So as I said, it's not about the results. It's I would say it's a view on how context is important in vision. And so just to summarize, if we look at the evolution of the image processing computer vision along the time, at the beginning we had this huge issue of semantic gap. You're extracting edges from images, and so what? How this related to your final goal, right? And then machine learning helped to get contextual, global context from the images. And then now deep learning, I think it's a huge change in this sense of context, because you can just learn representations that somehow captures the context, not only from one image, but from multiple sources of data. So that's what I am pointing to. I mean, data context, when you take video, audio, whatever, you can join and learn a representation that somehow captures the information that are in both modalities of data. And regarding the knowledge about the problem or properties related to the structure of the information, this, of course, is not new idea, but as I said, I think the question is, how do we incorporate this kind of knowledge in a more automated way in the modeling of the network or whatever? Because right now, many people do this, but it's very specific for each problem. So you do here, but you cannot apply directly to other problems. So is it possible to develop more general ways to do that? And also, so just to conclude, we need to thinking on solutions to computer vision problems. We need to work on at least these three contextual scopes, as I said, I name it then. So data context, prior knowledge context, and usage condition context. And I think there are a lot of opportunities, not only in the integration of this, but also in each of these scopes. So, as I said, no results, just a view. I think my idea here was to bring this and maybe have some discussions about how things you are doing fit in this or not, and so on. So thank you very much.
Okay.
Okay.
Okay. Thank you, Professor, for the talk. So now we have some questions from the audience. Do anybody has questions? We have raised their hand. Yes, go ahead, please.
Thanks for the talk and for offering all this sort of historical steps of computer vision. I teach so this is a question from an educator's perspective. I teach a course in computer vision, and when I get the feedback at the end of the term from my students, they always say that the early parts of the course are the toughest, which is the old school computer vision part, where they have to, you know, look at pixels and look at edges and find all these things, right? And what I think happens is there's a lot of tutorials and anybody can just go and run and train neural networks and things like that. But so anyways, my question is, do you still think it's important to teach this? What is the best way to cover it so that students understand why it is important and that it is still relevant? Or maybe the answer is it's not. And yeah, any advice on this how to teach the new generations about this old school computer vision techniques?
Okay, it's a very, very interesting question because I have the same question actually. Because I don't like this introduction to deep learning right at the beginning because, like you said, you just press the button and everything works. So that doesn't involve learning or understanding what's happening. And I think teaching this old computer vision is important because you have to understand issues like multi-scale variations, why that was the problem, why now it's not a problem or it's less problem. Because I think that will lead people to develop more interesting models, for instance. If you don't have that background, how are you gonna change anything? It's so I see a lot of works in deep learning where people just, I don't know, they change the architecture and beat the accuracy on data set. And so what do you learn from that? I think we learn nothing from that. So I don't know. So I like to teach my, at least show my students that the past is important. You have to look at the past and see what happened to project the advances to the future. That's my view.
Thanks.
But it's hard because it involves a lot of math, right?
Well, yes, it's a big chunk in thinking, yeah, rather than.
Yeah, deep learning you just need to learn the back propagation and that's it, right? Kind of. It's not that easy, but
At least in the sense of a short, like one-term course, right? Like the what they're going to do with, let's say, deep learning might not be super meaningful. So a lot of what they do is just grab a data set, train it, and here's my results, right?
Yes. So it's more engineering work than computer science, actually, right? Because you have to tune the parameters and.
Yeah, but two very quick things. One related with what Dino was saying is that I think as we are facing more challenging problems in deep learning, for example, we're talking about generalization. We have experience working in like a domain like domain generalization using very to disentangle content and scale. And in that case, using all techniques, many non techniques to deep learning techniques. For example, when we saw the 3D construction presented by so people is using image quality, for example, right? So people is going back to the old school. Second part is when you were showing the words, which I learned when I was in my lesson. My PhD student in here is working on car prototypes that the people is actually coming back to that because when you try to explain what a model is learning, you realize that they're learning like parts of the components. Yeah. Lots of people are doing that. They're going back to the other the formal part model. Yeah.
Yeah. Yeah.
This is the best model before the learning, right? Yeah.
Yes, I believe all the knowledge we have from the past is used somehow to build better models or to understand models, of course. So we cannot just throw away. And okay, just since you mentioned high-level information, I think one thing that will become more important now is graph-based models, graph neural networks, because then you can model high-level information. So this is something that I'm not working yet, but I plan to work very soon.
Okay, thank you very much for the question. I think we need to continue for the next session. Right?
Yep.
Okay, thank you, Professor.
Yeah, so like now we're going to have like four like next speakers, so like the speaker can come and stand in front. So we have like super superpixel guide load for improved multimodal segmentation in entropy. So Rafael will start, then it will come Daniel with the prototypical parts, is morphological cleanness quantification. Then we go Matias with zero-shot classification at different levels, and then finally we'll get one with towards characterizing the semantic robustness of face recognition. So I will measure the time like 7 minutes, and then I will just point out when there's like 2 minutes, so we can you can summarize, move forward. Just come to Rafael.
Yes.
Come here. So welcome everyone, our speakers. Let's check here the presentation.
I sent an updated version a couple of days ago.
Yeah, it should be here.
I mean,
So is this one, Rafael?
Should be, yes.
One.
We'll find out. Worst case scenario, I'll just skip some slides.
If you want, you can. If you want to edit it, you can.
This one works like.
Yeah, it's working. Yeah, just point. If it is not working, just point to here.
Okay, awesome.
Yeah,
All right.
just stay here.
Right, well, hello friends, my name is Rafael Martinez, and today I want to share some results from a research titled Superpixel Guided Loss for Improved Multimodal Segmentation in Endoscopy. And I'd like to begin by telling you a bit about a disease called Barrett's esophagus, which is a type of lesion that forms in the throat. And by itself, it's benign and symptomatic, but it can eventually develop into cancer. So early detection is critical. The way that you detect it is through something called an endoscopy. It's just visualizing inside your throat. And because it is asymptomatic, you detect it either to a routine endoscopy or when looking for something else, meaning you're not explicitly looking for it, which means it can be missed. Now, a way that a clinician can lower the chance that they miss these sort of things during a routine examination is that they can actually switch between lighting modalities. Nothing forces you to only use white light. And something like narrowband imaging or MBI can greatly heighten the difference between different tissues, including healthy and non-healthy. Now, for us, what could be interesting is maybe using techniques like binary segmentation to further help that clinician by describing which parts of the image the model finds interesting. But there's a problem. When we use different modalities with a model that has only been trained in one modality, the visual properties of the image change so much that the model degrades into something called domain shift. And furthermore, because these are medical images, we do not have enough information about other modalities to train a model that can perform well in all of them. So what we envision is maybe it would be better to do some domain generalization techniques in order to make a model that only trains in available white light imaging data, be able to perform in not only white light imaging, but in another modality that it has no information about, like in what we'll do in this presentation, narrowband imaging. Now, to do this, we envision using two techniques. The first one is called patch-based consistency, and the second one is called slick superpixels. Now, patch-based consistency is the idea of punishing results that have patches that are unlikely to be correct. Now, a patch is a hole or a discontinuity found within a mask, and it may be correct or it may not. If that was like a mask of a Swiss cheese, then of course, we would expect it to have holes. But for Barrett's esophagus, not only are patches not too common, they tend to be small in size. And even if we don't punish correctly 100% of the ones that are incorrect, by punishing the ones that we believe are incorrect, hopefully the network will learn shapes that are more applicable over multiple modalities. Now, the other idea is using slick superpixels, which superpixels are just groupings of pixels. But what is interesting is that by using a technique like slick, we can use functions that incorporate color information. And color is particularly important for Barrett's esophagus because regardless of what modality you use, lesions will be different color than healthy tissue. So if the model can not only identify colors, but boundaries between colors, a network will hopefully be able to use that information, which is domain agnostic. It will not depend on what modality of light we use. Now, to do this, we envision the use of a compound loss function. Now, part of it is using cross entropy, and the other one is using something we call a superpixel guided loss, which will do two things. First, it will encourage the model to follow color boundaries, as you can see in that blue check mark. And the second is that it will punish results that either don't follow superpixel boundaries or fail to account for a significant portion of the superpixel, which could be due to noise or could be due to patches. You can see in that red circle. Now, to test this idea, we used a dataset called EndoUDA, which contains Barrett's esophagus imaging from both white light imaging and target domain, and we only train in white light imaging. First, we run a baseline using unit, attention unit, and efficient unit.
And we run first some results only in the source domain. We can see that unit performs the best. And then we switch over the model without any other training to NDI. And we can see that the models suffer extremely. There is a degradation across all models, which shows how much domain shift can harm your models in these scenarios. Now we grab unit, which was the best performer, and we do the superpixel augmentation. And to do that, first we have to adjust the hyperparameters for superpixel generation. And we're focused on two main parameters right now, the number of superpixels K and the compactness N. Now, the more superpixels we have, the finer of color details we'll be able to explore. But if the superpixels are too fine, we'll actually end up segmenting individual points of noise, which will mean patch-based consistency will not work. So we want to find a good trade-off for that. And for compactness, the lower the compactness is, the more we allow the method to follow color freely, which means the color boundaries will be very accurate, but also could be very noisy. So we want to avoid that, and again, find a good trade-offs. Final values, 550, we found work well. And before I show you the quantitative results, I want to show you some qualitative results. So here, I want you to particularly focus on these results from the source domain and these from the target domain. Notice how our model is less likely to have noisy boundaries because it likes following color boundaries. And it's also less likely to have little bits of extraneous objects around the lesion because those are very likely noisy or patchy. Now, quantitatively, we notice that our model is a little bit worse in the source domain than unit, which is expected. One of our methodologies is regularization. But does it pay off? The answer is yes. Not only is the drop much lower when using this technique, we actually have a gain of around 20% compared to the best performing model, which is unit. And well, we consider this significant. So what can we learn from all of this? First, domain shift is bad, and we should probably be thinking about it for these sorts of problems where different modalities could be involucrated. The second one is that superpixels, which we're talking about some old techniques, can incorporate this domain agnostic information that may be applicable across a whole task, like this idea of color boundaries. And finally, that this method applied to unit, as you saw, had significant improvement, and because it is a loss function, it can be made to have no effect during inference, which is super great for speeding models. Now, just a very quick couple of future work suggestions. First, Slick is a relatively primitive model. Having more advanced superpixel generation methods may be able to incorporate more complex data, which could broaden the amount of tasks this idea could tackle. Finally, the primary team was a bit of a headache. So if we had some end-to-end training ideas, or if we could find a metric for a more quantitative-based adjustment for these parameters, that would be awesome. So if you want to discuss this further, you can find me in the poster session. But for now, that is all for me. Thank you.
Thank you very much. So then let's welcome Daniel. It's the presentation. Yeah, just check what's the right one for you. Yes.
And puedo presentar PowerPoint, ¿verdad? Es la aplicación.
Te aviso cuando te queda.
Okay. Well, today I'm going to present our work, which utilizes prototypical parts for classifying different types of kidney stones and to use morphological analysis of these kidney stones. So the agenda for today is the analysis, a little bit about this case of the kidney stone morphological analysis, how deep learning is used recently to automatize partially this task, and actually how explainable AI is leveraged to enable a better implementation of deep learning in this task. And finally, how our work is, enabling a little bit of this, solving some of the issues of explainable AI at the moment. So in general, the analysis of these kidney stones are visual analysis of the surface and section of the stones, and actually also analysis with a Fourier transform infrared spectroscopy of the dust of these stones. But this process is very long, can take up to a couple of weeks or even a month, when a patient can generate again, in some cases, in a couple of weeks, another stone. But patients have to wait for a diagnosis. So the proposal recently is to use deep learning models and other automatic techniques to give a recommended classification of the kidney stone. And here we propose that that will be able to be done if we also provide the specialist with enough information for this classification, like where the model is looking and which are the visual characteristics that produce this classification. So we can think that we would want to automate this task, but at the same time, since deep learning methods recently are very good at very different tasks, that's one of the reasons. But we have to take care with the downfalls of these models, the catastrophic errors that some of these models still are sensible of. And since these models have these kind of mistakes, it has also been stated on the literature that those should be computer-aided, not automated, mainly because of this type of serious mistakes. So here is where explainable AI is come to the rescue, since it's an area that will help us to analyze why the output of a model, what the model has learned inside of it, and if it can handle of all possible cases. So we also work with the visual data. And in this area, there has been some good applications of explainable AI on medical images as well. Yet again, explainable AI has its limitations, like lack of faithfulness. This is some methods that explain you why a model classifies a certain image in a certain way are not reflecting what the model learned inside of it. Or a lack of stability, for example. We can perturb a little bit the input image, and then we get a very different explanation, although the output classification of the model is not changing. Because of these limitations, we are proposing to change, and instead of only using a heat map for the classification of the model, well, we are indicating where the model is looking, but also the most similar case from the training set that our classifier is learning. So cases that the model has learned to be useful for the classification of the input image. So these are part of the model. And also we are giving some visual characteristics that these parts are looking at, like for in this example, contrast. And well, with this enriched information of why a model produces a certain classification, we will be able to enable a specialist to do this analysis of kidney stones in a better and faster way. The general idea is we are learning parts that constitute a class with our model, with part prototypes. And these part prototypes will tell us the level of similarity that the model is finding between the example parts and the parts in the input image. Also, what are the main visual characteristics that each prototypical part is looking at? And this number of prototypical parts per class is a hyperparameter, but we can give an explanation for each of the prototypical parts that the model is looking at. Well, that the model has learned, sorry. So we can analyze the actual output of the model and see what its activations were, how similar the model judged to these parts to be on the input image. And also we can compare these activations for each of the different classes. And here you can see that the 9.2 on the top right is the highest. So also in this case, our model is very confident that this is a correct classification. Not that it actually is, but this information should be enough for a specialist to know. Well, this information is enable us to also characterize the model in a general way. And it has enabled us to analyze certain cases on a high dimensional space. Why the model committed had certain mistakes? Well, in this case, that we can find which of the visual characteristics are responsible for this behavior. So usually explainable models lose a certain level of performance. And in this case, we don't lose as much. And in one of the modalities, we even get a model that is the best. Also, something surprising for us was when we perturb the images, the performance of the model, in our case, when using the prototypical parts, were best. Well, those were the best models by 3 and 5% in accuracy and F1. Well, I don't have much time with this, so I invite you to check the poster and chat more in the poster session.
Thank you for the presentation. And now we have like Matias that is going to present the zero shot classification. Matias. Here. Yes, this one, right? Sí.
Thank you.
Hello, my name is Matias. I'm from the National University of Córdoba, Argentina. And I'm presenting zero-shot classification at different levels of granularity. And I would like to start by defining zero-shot classification as a task of learning predictors for classes not similar in training, which means that the set of categories for train and test are the joint sets. One popular approach to address this task is to use a new level of information and actually information to describe the categories, all the categories involved in the problem. In this image, we can see two different spaces, the visual space or image representation space, and also the semantic space that we are using, in this case, binary visual attributes to describe each concept. We also have a bilinear compatibility function that essentially learns how each image agrees with each concept. This function, as is bilinear, we can go from one space into the other. We can project the visual space onto the semantic space, and also the semantic space onto the visual space. The main questions of this study, I mean, the question that I'm trying to answer is what is the impact of the data granularity when zero-shot classification is performed? Also, how to obtain data sets of different granularity with a suitable semantic space, if you want to corroborate the previous question. And finally, what is the relevance of the visual and the semantic space during the classification problem? The proposal is to create synthetic data sets with a parametric granularity, and also to define a model to optimize the classification, but preserving the visual or semantic structures to see if one of these spaces are better than others. Okay, to do that, I am encoding the structure of the visual and the semantic space using the similarity between its elements. In the case of the semantic space, it's easy because each category is represented by one vector. In the case of the visual space, I'm taking the average per class as a visual category, and then I can compute the similarity between all of them. These structures, we can compute this structure before and after the projection, so we can see how all the elements of, for instance, in the semantic space are related before and after being projected onto the other space. Moreover, we can define using the element-wise product between these two structures to highlight the elements that are well represented in both spaces at the same time. And finally, the optimization is defined using maximum marking classification. Actually, this is structure support vector machines with a new term that aims to control the structure of the visual space or the semantic space according to the three different models. And the first is just trying to keep the initial structure of the categories that are well represented in both spaces. And the other two definitions try to use one of the spaces as reference to the other. For instance, I can project the visual space to the semantic space following the structure of the semantic space. Okay.
The synthetic dataset is generated by the use of the Gaussian algorithms, but initializing this algorithm with the center of the well-known datasets in zero shot, because I want to use the semantic space provided by the dataset. In this case, all the experiments that I run are using the BERTS datasets. And I am also including a scalar factor to control the granularity. When this gamma is big, the granularity is more coarse. Okay. Well, this is just a sanity check to verify that the scalar factor is actually controlling the granularity. And after running the different experiments over the different models and using different data granularities, you can see at the bottom of the table the average and the standard deviation. And S1, S2, 3, and 4 are different class partitions for train and test. If we see with details, the standard deviation compared with the scalar factor, I mean the granularity, we will find there is a strong correlation between the granularity and the variability of the performance. We see the plots, we can see as gamma increase, the variability is also higher. Okay, so in all the methods, we can see a strong correlation between the granularity and the performance variability. As a conclusion, well, maybe the most important conclusion is the strong correlation between granularity and variability, particularly in the coarse-grained datasets, because it could vary the selection of one method over another in practice. Respect to the roles of the semantic and the visual space, identified which is the best space for the classification. I think that both spaces are important, and actually I think it must exist a optimal combination between them. And as a methodological conclusion, well, this study suggests that data granularity is an important characteristic to obtain a more comprehensive evaluation in zero-shot classification protocols. Well, thanks. Thank you. Thanks. And now welcome Juan with our last presentation, and we have like all the Q&A at the end. So this one, right? Unified. Yep. Yeah, go ahead. Thank you.
Hi, everyone. My name is Juan, and today I'll be talking about some work we did on characterizing robustness of face recognition models. So what is a face recognition model? Essentially, right, it's an input-output system, right? You give it a face, there's the recognition model, and then it says, oh, I've seen that person, that's Andy, right? Of course, we're interested in them not being just good at recognizing Andy, but multiple people, right? So you give the face of this person, and then it says, oh, I've seen that, that's Alex, that's Anna, and that's Arnie, right? Now, in this work, we are interested in these models because they have remarkable performance. So we are interested in saying, when do they fail, right? Not just when they do good. So in particular, would it be possible that, for instance, that's Andy, right? But then one day Andy changes his glasses a little bit. Maybe he has a little bit of a smirk. And then the model now says, oh, that's Bob, right? Can this happen? And if, of course, this would be a huge problem, right? Does this happen? So we focus on when does face recognition fail? And in particular, can we find patterns in the images in which it fails? Why do we think this is possible, right? Well, because in computer vision, we have repeatedly seen that deep learning fails unexpectedly. And in particular, there are these things called adversarial perturbations that mean that whenever, well, sometimes when you input, you manipulate the image, the input image in a particular way, then the deep learning model can unexpectedly fail. This is traditionally seen as you have like something like a cat, right? The model says 88% sure that's a cat, but then you just change the cat by some imperceptible perturbation of some pixels here and there, and then the model is 100% sure it's a guacamole, right? It makes absolutely no sense. So of course, these are interesting in themselves, and they have attracted a lot of attention across our field. However, that's not what we are really interested in, right? It's not just adversarial perturbations. We would like something more like semantic perturbations. So we want Andy, right? And we want to perturb Andy semantically, right? Changing his glasses, changing his smirk, or something of the sort, such that it originally said Andy, now it says Bob. Right? So we want semantic perturbations that also preserve identity. So how can we find them, right? How can we computationally generate them? Of course, it's a very hard task, as I can see from your faces. So in the case of our work, we leverage GANs, right? Generative adversarial networks for this task. And why? Well, because they can generate amazing synthetic human faces. So StyleGAN in particular is one very famous GAN by NVIDIA, right? And StyleGAN is essentially an input-output system, right? You give it an embedding in some embedding space, right? And then it generates an image. And I think I messed it up here because I sent the PDF and not the PowerPoint presentation, which has a nice video. So please just imagine that I'm walking in StyleGAN's space, and so you can like see a smooth interpolation of the person's face. So say, amazing, right? So we are gonna use this property of StyleGAN, right, of having this smooth embedding space to search for these people. So let's say you have this input point that's called that W. You have your StyleGAN, right? So you push it, you push W through the StyleGAN and you get this person, right? So we are searching for some perturbation that's called that eta, such that you get this W prime, right? And then when you push this W prime, you will get another person, right? Close to what we want, but not really what we want. So we need to constrain the perturbation, right? Such that it does what we want to do. So we need constrained perturbations in latent space, not just any perturbations. In particular, we will take the approach of having two types of constraints. One is direction constraints, right? So in this space, where can you move to? And magnitude constraints, how much can you move, right? So direction constraints, we are searching for only changing certain attributes of the person, right? In this case, we will be focusing on age, pose, gender, eyeglasses, and smile. So 5 attributes right there. We codified this information into some matrix V. And so that corresponds mathematically to just saying, okay, this is like part of the column space of this matrix V. And in terms of magnitude, we want to think how much can we perturb each of these 5 attributes, right? So there's like a small quantity which you can move along this the dimension corresponding to this attribute. We codified this information into matrix V, and then the corresponding constraint is simply something like the norm, but with respect to this matrix M. So you have W, you have W prime, right? So the direction constraints is equivalent to having to only walking along a certain subspace, right? So imagine kind of a plane in this case. And then the magnitude constraint corresponds to extending a particular ellipsoid on top of this hyperplane, right? So how does it look like in practice? If this is your W and we start sampling from this ellipsoid, this is kind of what we get, right? So for instance, you can see that people are changing, I don't know, the glasses, or they smile, or they change a little bit their pose. So what's the general pipeline? You have StyleGAN's latent space. You have the latent code. Let's call this person Alice. You push it through StyleGAN, so you get the image of Alice. Then you define the subspace, you define the neighborhood, and then you sample some other point here, right? So we will call that Alice star, right, or W star. We push it, and indeed, it's someone that looks like Alice, but without, I don't know, the glasses or something. Now we push this through a face recognition model, which is essentially just mapping each of these images into some face embedding space, and it's then computing nearest neighbor, right? So just by finding which image is the nearest neighbor to Alice, it will recognize Alice, right? That's essentially how face recognition models make matches. So as you can see, it's entirely differentiable, right? We map from the embedding space to the image to the face embedding space. So then we can backpropagate just loss.backward, and we optimize for the eta. So summary, we work in Stalkans latent space to generate realistic faces, and we introduce two types of constraints, right? One direction that is related to attributes, particular attributes, and then magnitude. How much can you modify this attribute? Now, of course, your question is, well, can you fool it indeed just by doing this thing? Well, yes, we can, as Obama would say. So we have A, for instance, this kid in particular, and this is an A star, right? This person modified that we can find whose nearest neighbor should be this person. But if you ask the face recognition model, now it says it's this other baby. Of course, we can find this systematically across our dataset, which is, I think, a very cool finding. Okay, so once we see that we can indeed fool these models, we are also interested in, well, can we find patterns in which are the attributes that the face recognition models are paying attention to, right? So the attributes importance. So in this paper, we also propose and execute a statistical procedure for interpreting attributes. So in this case, we just took three very famous face recognition models, and then we rank how important do they think each of the 5 attributes we considered are taking into account for the recognition behavior. So in particular, I think an interesting thing is that all of them think eyeglasses are very important. I have 2 things to say here. Well, this happens, I think, to us, to humans, right? Whenever we are very accustomed to seeing someone with glasses and they take them off or they put them on, it's kind of difficult, right? And I guess it also makes kind of sense then that Clark Kent can just like put on the glasses and it goes unrecognized. And the last thing is the smile. Finally, we also think of certification, right? So these systems, as you can see, they are kind of brittle, right? And not just in the pixel-wise sense, just moving pixels here and there, but actually with respect to some attributes, right? So their outputs are unpredictable. So we are thinking, can we certify that these systems will not change their decision whatsoever, regardless of the perturbation? And well, turns out that yes, we can. With the framework I showed you here, turns out this framework is very amenable to something called randomized smoothing, which is a paradigm to certification that is used in certifiable, in the field of certifiable robustness. In particular, let's not go into details, but essentially we will just be moving again along our subspace, and we will be randomly sampling from this subspace. And turns out that if you do this expected value of the classifier of the face recognition model, turns out that that is certifiable just by doing this Monte Carlo sampling. Yes, so this is the definition of the certification experiment. And again, we see very consistent performance across the same face recognition models we had studied before. So summary, we propose a methodology to characterize the semantic robustness of face recognition models. We characterize their adversaries, right, in terms of the attributes, and we also studied the certified robustness of these models. Thank you very much.
Yeah, like now, what the speaker can come to the front, so we can get like 9 minutes of questions. So I will go one by one, and then we can get like collected questions. So thank you again for all like our 4, yes, our 4 speakers. Yeah, thank you very much. So yeah, let's get some question for Rafael, like super pixel guy lost.
Yes, I understood the importance of the color. But what happened in the scenario, for instance, where the image, because of the illumination or the shadow, what's happening in this case?
So that's, I would consider one of the main limitations of my work, that the superpixel generation method really only takes into account color. Well, I mean, it takes into account also the distance between pixels, like most superpixel generation methods. But because it's called SLIC, simple linear iterative clustering, can only really describe color once you start getting into tasks that either are not just color dependent, polyps are a big one, for example, or when you start getting images that are very difficult to just look at the color by itself, the method can fail. So for that scenario, I do consider important to explore other superpixel generation methods, so we can incorporate information that is not just color for this sort of system. But yes, that is an excellent point, and the system can absolutely fail once you start removing the color importance from the test.
Great, yeah. So like, here's a question for Daniel, like, there is any question for the digital part, the LatinX classification? Anyone have a question? Yeah, I have a question for Daniel here, like how, like for those explaining the AI work, like, like how we can go like behind, like beyond this heat map and like similarity case to use also some multimodality and language model to actually do interpretability in the language space. So you can actually, instead of just showing the heat maps and the, like pointing out where similar stuff, like how you can kind of explain somehow that's what's happening and, like what's going on, if you get some thoughts on that.
Yes, actually, even on some talks with other researchers, there have been some comments with really different advancement with large language models that possibly, this is just a possibility, that these models, if they were like a chatbot that you could interrogate about a certain case, that you get more information under demand by the user, then that would be great because you are adjusting the level of detail that the user needs. That's a very promising direction. Yet, how to do it is not very clear. One way to do that is to, has many multimodal approaches so far have done, is to match the embedding space or the high dimensional space to be able to have a same representation for the image, and that can be translated into a textual description of it. Yes, that will be the case.
I see that's very nice. It's kind of, so there is another question for Daniel, like in the, so yeah, then we can get some questions for Matthias, like the zero shot classification at different levels of granularity. There is any question? Like someone have question for Matthias, like any doubts on that or any questions? Yeah, so yeah, I have like a general question on that, like like in the zero shot for classification for different levels of granularity. So mainly, yeah, when you define the granularity, like it can be done in a different way. Like, can we use like some foundation models to kind of leverage that or learn that type of, yeah.
Another way to create the different type of granularities.
Yeah.
The main problem with it is if you use, and you can use any generic model to generate a space data set, but the problem here is for zero shot you need to have a semantic space to understand how the known classes and non-cal classes are related. So in this case, you can use any algorithm you want, but what I did here was to use the centers of the visual space of a well-known zero-shot dataset to initialize this algorithm. In this case, I can use the semantic space provided by the dataset itself. So the answer is yes, but you need also to obtain a semantic space representation of the categories.
Yeah.
Am I answering?
Yeah, like it will get biased by that data set that you use for training, like because yeah, if you get that semantic in those specific data set, your model is going to get some bias.
Yes, I decided to use just one data set because the idea is to extend the experiments using all the data set of the literature. But I've been using in general the data set that I've been using zero shot are from 4 to 6 with more or less popularity. But I decided to use the BERT dataset because it has more categories and knowledge, and it's also considered a fine-grained dataset. But we can use all the dataset we want in the literature.
Yeah, nice. Yeah. So thank you, Maurice. So yeah, finally, like question for one, like like the paper recognition of the listeners, like if there is anyone have questions.
You show that you can, you show that you can modify full semantically your model, like using examples. There is a way of protecting the model, like in advance, if you know, how you thought how you can protect those kind of systems, like.
Yeah, so like the direct equivalent of doing this, but regardless of whether it's changes in pixels or in actual semantic attributes, would be just to simply random around the neighborhood, right, and retrain on this example.
Like this is very consistently improving the performance of many models in certifiable robustness. So that would be like the first baseline I could think of. Beyond that, I think it's usually very hard, like trying to predict when these models will fail and doing something about it. Like the current best thing that we have is adversarial training, right? Which is exactly like, it's kind of what I'm saying here, right? It's not just randomly something, but actually computing the direction and training on the adversary, which is extremely expensive. So I'm not sure how that will scale. But my current best shot at it would be, the current trend of training on 400 billion images and see what happens.
No, right.
Yeah,
Can I make a?
Well, you can go first after this.
Okay, so you are training on these synthetic examples. When you are testing, are you testing on actual real data? Because if you are biasing your model already to this synthetic image generation stuff, there is a domain gap between the real stuff and the synthetic stuff. Even when we look at it, and it looks qualitatively, it looks very similar or the same. But actually, in a computational prediction, it's actually different. So, are you testing in the actual real world data?
So our whole paper is on test mining. Like there is no training anywhere, but the only training will be the ETA that is optimized somewhere. So these are just off-the-shelf models that whose weight we downloaded. So there is no training there. However, going like to your question, all of this is on synthetic data because eventually, like, you need to be able to manipulate the latent space of the GAN, right? So we use synthetic data. You could also like take a bunch of images and invert them right to the latent space to be able to go along this. But no, this is all synthetic.
Great. Yeah, let's say just one more question and then go for, we are running after lunch. Yeah, and then take a picture after before going to lunch. Yeah, so we'll
Nice presentation. I was wondering how would you handle our type of data sets that are not from places? How would you choose the latent space of style guide, let's say? How would you perturb each of the features of the pattern to see that, I don't know, so move this to another type of data?
So it's very hard. Right? That's the short answer to your question. But I guess like the baseline thing that I would think of is, so for instance, in our work, what we did was we found these directions, right? So you move in the direction of a smile, the direction of a glass. And where did I come with this direction? It was from another paper. It's called Interface GAN. And essentially it's just like how to discover the directions that correspond to semantic attributes, right? What people do is essentially something like PTA or regression from what you're moving in latent space, you generate an image, and then you have like some attribute classifier for faces, right? So you try to find what is the direction here that generates changes in the classifier. If you have the equivalent thing for some other domain, right, I don't know, then you have like houses and you have a classifier for the style of the house or something of the sort, then you can kind of repeat this procedure. But again, it will always be like very domain specific. But in a sense, I think it should be very domain specific because like attributes may not exist, like the same attributes may not exist across the net.
Yeah, thank you. So thanks again, our speaker.
We thought of taking a group picture outside on the stairs. So we
They can put a picture, no?
did you all take a t-shirt? Please feel free to take one of your size from the table.
Yeah.
And we can go to the stairs. So we have the nice earth and the logo with us.
We grab the t-shirt.
Hola.
Mucho gusto, Daniel.
Muy buenas.
Bueno,
¿Qué tal? Un gusto volver.
¿Cómo fue tu viaje? ¿Todo bien?
Sí, todo muy bien. Te iba a
¿Quieres usar
preguntar.
la tuya?
Sí, y
Vamos a
quiero,
hacer
quiero
eso.
probar antes.
Sí,
¿sabes?
sí,
Porque si no,
ahora
no.
podemos probarlo todo.
Perfecto, aprovechando.
Sí, a esto algo que no había considerado.
Bueno, está mi chica aquí. Entonces vamos a tener menos tiempo para comer nosotros.
Sí.
¿Una manzana?
Sí, ahora.
Hay una sesión de cosas. No, de hecho les vamos a. Yo tengo unos cuentos pinchos.
Ahí, en la sesión deben haber muchos también. Ahí donde están, me imagino que deben tener algunos. Yo creo que lo podemos poner con los pinchos porque vas a estar ahí y cuando tengamos los recoges.
En caso de que sea necesario, tengo pinchos, sí.
Yeah.
Hello. Please start taking seat if you are staying for the talk. We will proceed with the next session. Yeah. Well, let's go for it. We welcome Miguel Ángel Bautista. He will be giving the talk that he will mention himself. Let me tell you a bit about him. He is currently a research scientist at Apple, where he carries out research in machine learning and computer vision. His current focus is on developing generative models that make as little assumptions about data as possible. But before joining Apple, he held a postdoctoral position at Bjorn Ommer's lab, where he led several research projects around self-supervision in deep learning, as well as the first forays into generative modeling, that is the pre-stable diffusion. Miguel got a PhD in machine learning in 2015 from the University of Barcelona. He was advised by Sergio Escalera and Oriol Pujol. And he was back then working on learning error correcting representations from data. He spent a good part of his PhD at Carnegie Mellon University working with Fernando de la Torre on matrix factorization models. So please, the floor is yours. Thank you for being here.
Thank you, thank you, thank you. That was a very nice introduction, Stefania. Thank you very much. Thank you everyone for coming over today, especially after the lunch break on the first day. This is where jet lag hits the most, I think. So I appreciate that you're all here. Today we're going to talk a little bit about the work that I've been sort of like leading at Apple on this idea of generative modeling from like images to functions and manifolds. And we'll see what that means. So let's go ahead. Well, I'm just going to briefly mention, I'm a scientist at the Apple Machine Learning Research Team, that's currently led by Sami Bengio. I've been at Apple for a little bit over 5 years, working on a variety of topics from metric learning to 3D reconstruction. And more recently, for the last sort of like couple of years, I've been working on several topics around generative modeling. And I worked a little bit on that when I was a postdoc at Bjorn Ommer's lab, but you know, they got their fame after I left. So here's the agenda for today. We're going to be talking quite a little bit about diffusion generative models. I'm going to introduce this idea about thinking about data samples really as continuous functions. And then we're going to see what happens if you truly sort of like stick to that hypothesis and try to formulate a generative approach. We're going to see two examples of what that would mean. And finally, we'll wrap up with some conclusions. So I think it's not a secret really that generative models have driven impact in ML for the last few years. In particular, we've seen great applications for generative models of sequences that will be like large language models, but also 3D protein structures. But then more recently with the sort of like advance of diffusion models, we have seen a lot of development on text-to-image models, video models, and so on. So, you know, what we're going to talk about is sort of like the core question, this P of X given Y, right? And how come we have a different architecture for each of these domains, and what can we do if we sort of like wanted to formulate a grand unification of this problem in a sort of like a data agnostic way? So let's get into it. Before I start, is anyone here, or does anyone here has not heard about diffusion generative models? Please raise your hand if you haven't heard at all about diffusion generative models. Great, so I can go over this very quickly. So in diffusion generative models, we have two processes, right? We have a forward process that takes data and adds a little bit of noise for a very long number of steps, right? And therefore, sort of like destroying the structure in the data. So think about data here as X0, that will be images, for example. And what the forward process does is it adds a little bit of Gaussian noise for a very long number of steps. Think like 1,000 steps, right? What happens effectively is when you reach t equals 1,000, you have destroyed all the structure in your data, right? Your sample is indistinguishable essentially from a sample that's drawn from a Gaussian. So that's the forward process. That's how you destroy sort of a structure in the data. And then the reverse process is the generative model itself, right? And what diffusion generative models do is for every step in the forward process, they learn to approximate the inverse step, right? So as opposed to destroying the structure in the data, they learn to generate the structure in the data, right? So that's sort of like a very broad description of what diffusion generative models do. So let's go a little bit more into the details because there's a couple of things that I would like you to have or to keep in mind. And let's take the case of denoising diffusion probabilistic models, which is sort of like the implementation that's sort of easier to grasp. So what happens during training of these diffusion models, right? During training, what we do is we say, well, you know, if I pretend that my forward process is Gaussian and there's some constraints around the kind of noise that I can add to data, but what I can do is I can compute the forward process up to a particular time step t in a closed form, right? I can compute that really fast. So the training algorithm really what does is, you know, it samples some data from your empirical distribution. That will be Q of x0, right? So you have a training set of images and you sample some images and you sample your only, right? And then you sample some noise. And what you do is you compute a linear combination of your data x0 and noise. And that linear combination is weighted by parameters that tell you how much noise there is up to time step t. Right? So this linear combination, you know, you can compute that in closed form and you feed this into the model. The denoising model is epsilon theta, right? So the denoising model sees a noised version of the sample, right? And it tries to recover the noise, right? So again, during training, you sample data, you sample a time step, you sample noise, you linearly combine noise with data, and then you train a network to recover the noise. Right? That's all you do. Turns out we know how to do this very, very, very well, right? There's no instability. This is like in GANs and so on, right? So that's sort of like the training process. So what happens during inference? Well, during inference, what you do is you start at time step capital T, right? That's where you had it. You had all your noise, and then you're trying to denoise that. So at time step capital T, you draw from a Gaussian distribution, and then you basically feed that sample into your denoising network, which is also conditioned on the time step T, and that gives you sort of a prediction of what is the noise that sample has, right? And then you subtract that noise iteratively, so you run the reverse process, and at the end, what you get is a sample from the approximated distribution, right? So that will be, in this case, P of x0. So that's sort of what happens during training and during inference of diffusion models. And there's, you know, great success recently for all signals that are sort of like defined on a grid. So for 2D images and even for long form video, we have great models. And when I say we, I mean the community, not necessarily me. But, you know, again, these models work really, really well for images and for video. So the question that, you know, I ask myself is, can we generalize these models to work on any kind of data? Not necessarily just images or videos, but any kind of data. And I mean this in the broadest sense possible. So what does that mean, right? So, you know, let's pretend for a second that, you know, we are going to train a diffusion model and we're going to train it on images that are 640 by 480, right? But, you know, you may as well say, well, you know, this is just a choice of resolution that I made. This is an arbitrary decision. I could have also trained it on resolution, right? And the same images, right? They're just sampled at a different resolution. I could train it at a very high resolution, almost HD, right? So what happens at the limit, right? What happens if you want to train a diffusion generative model with samples that have infinite resolution, right? What happens in the case is that data really becomes a function. And for the case of images, at the limit, an image is a function that maps pixel coordinates to RGB values, right? And it's a continuous function. You give the function a pixel coordinate, a 2D pixel coordinate, and it spits out an RGB value, right? And observing different resolutions is just, you're looking at this continuous function and you're sampling at a different rate, right? That's how you get different resolutions of the image. But what exists is this continuous function, right? Cool. So then, once you believe this, then the natural question to ask is, well, isn't this really true for any kind of domain? Like, can we just pretend that everything is a function and just design our model in that way, right? So for example, what do I mean here, right? So I said for the image case, right? You can pretend that an image is it's an Euclidean grid, right? That has W by H pixels. And for every pixel, we have a three-dimensional value. But you can also pretend it's a function, right? A function that maps R2 pixel coordinates to R3 RGB values, right? Same thing true for videos, right? Videos can be W by H by time, right? So you have this three-dimensional grid. And for every element in the grid, you have an RGB value. But, videos are also continuous functions that map R3 elements to R3, right? It maps a coordinate, spatial coordinate and a time token to an RGB value. Same thing is true for 3D geometry, right? So for virtually for any domain, you can express data of that domain as a function, right? And the question here is really, well, us being curious and inquisitive researchers is like, well, Miguel, why should I really care about this parameterization? Like, is there anything interesting at all? We have convolutional networks that work really well for images and for videos. So why should I care at all about this functional parameterization? And I guess the interesting bit of this is that once you pretend that everything is a function, you can do things that you wouldn't be able to do otherwise. Here's an example. This functional parameterization is shared across a bunch of data domains. So one thing you can do is you design one network architecture, and then you can use it to train generative models for images, for 3D geometry, for video, or for very sort of like exotic data types for functions that are defining curved spaces. And we'll see how you would go about that. But it gives you a very natural shared data interface, right? Because you express everything as a function that maps elements from some kind of geometry. It could be R2, it could be R3, it could be like a curved surface to some signal space. And all data domains can be expressed in this way. So you can even do things like train large-scale multimodal generative models with a single network architecture, right? You don't change the network architecture at all. Cool. So, these general observations that I just described were sort of like the motivation of our initial work on this direction, which we presented at iClear a couple months ago and was led by Pei Yeswang, who was an intern with me last summer. And the idea here is, well, okay, now that we believe this sort of like functional parameterization of data, how can we efficiently formulate and implement a diffusion generative model for discontinuous functions, right? And now we are aware of the challenges, right, of this sort of parameterization, because I mentioned at the beginning, this functional data is infinite dimensional by definition, right? So how do you even represent infinite dimensions in a neural network, right? That's weird to think of. We also don't have an analytical form for these functions, right? For images, it's very clear, you have your W by H grid, but you don't have an analytical form, analytical expression for an image that, given pixel coordinates, spits out RGB values. So how do we sort of like design our model around that? And also, we can now rely on the almighty unit that is used in diffusion generative models. I don't know if you have trained a diffusion generative model, but if you try to change the unit architecture into something else, everything breaks up completely. So, what are the options, right? What can we do about this? So let's get a little bit more technical. So before diffusion probabilistic fields, the traditional way that you would think about this would be something like, well, let's pretend that I have a collection of images, and each image here is a function. And you may have heard the term field as well. I use field function exchangeably. But you get access of a bunch of images, right? And what you would do is, for DPF, what you would do is you would train a little MLP for every training example. And this MLP would map pixel coordinates, to RGB values, right? And then the weights of the MLP will be used as a sort of proxy that encodes the image, right? Because you train one MLP for each image in your training set. And then after you've done that, you collect all the weights of all the MLPs, and then you just learn a generative model for these weights, right? So these are two separate training stages. The first training stage, you fit an MLP to each training example in your data set. And then on the second stage, you learn a generative model on top of the weights. And so if you may have heard this being called an implicit neural representation. If you have heard about NERV, this is what NERV is, right? It just takes as input an point in R3 and a camera direction and spits out RGB and density. But that sort of field representation goes well beyond NERV. It's sort of a fundamental quantity that expands all domains, not just 3D geometry. So that's sort of like the implicit neural representation way of dealing with it, which has these two training stages. And when you train the probabilistic model, the gradients of learning P theta here don't backpropagate to the MLPs. Those are two separate training stages, right? So what we thought of was like, okay, can we just do the complete opposite? So instead of using this implicit parameterization, we're going to go the explicit way. We're going to say, we're going to define a function, f here that maps pixel coordinates to RGB values with a set of input-output pairs. All right, you just give the model an input, you measure an output, right? And you do that for a bunch of points. That's sort of like a set parameterization of a function, right? And it's giving you the explicit rule that maps pixel coordinates to RGB values, right? So that's we call this sort of like a context parameterization, but in a sense, it's just a set of coordinate and value pairs. So for images here will be a set of 2D pixel coordinates and RGB values that are attached to it. And then what you would do is you would say, well, I want to learn a generative model that's conditioned on this context, because this is sort of like the function parameterization that's explicit. And I want this probabilistic model to predict for me a distribution over RGB values given an XY coordinate of a pixel. Right? And you can evaluate this distribution for any XY that you can think of, right? So this is a continuous function over XY. So that's the difference between explicit and implicit parameterization. So how do you take this explicit parameterization and then sort of like put that into play when you're training a diffusion model? So the idea is actually simpler than it looks like. So let's stick to the image case, right? We went through the training algorithm for diffusion models before, right? So we're gonna go over the differences, right? So we just sample images, in this case functions, from your training set, and then you randomly draw a bunch of pixel coordinates and RGB values from the image, right? Part of them are going to be your context pairs. Part of them are going to be the orange dots here are your context that defines the function, right? And the purple dots here, the query pairs, are the points at which you want to predict noise, right? So what you would do is the following: get an image, sample uniform context points and context pairs and query pairs. And what you would do is you train your denoising network to predict noise for the query points given the context points. And so we turn this model into sort of like a conditional model. And these query points here are continuous, right? You can just say, I want to evaluate a particular pixel coordinate in my image. So the one way to intuitively think about what's going on here is in the standard diffusion model, the output of the network is a denoised sample, right? Here, the output of the network is really a denoising function that can be evaluated continuously in the pixel coordinate space, right? That's the main difference. And the way you do that is you turn the denoising network into a conditional denoising network. During sampling, what you do is, again, very, very similar from the standard DDPM. The only difference is that you start by defining the coordinates at which you want to evaluate the function that you're generating, right? So for an image, you say, hey, I've trained this model and I want to generate a 64 by 64 image. So what you would do is you would densely define 64 by 64 pixel coordinates, right? And then for each of those coordinates, you will attach a sample from a Gaussian distribution, and that will be the query points at time step capital T. And then what you would do is you would say, a subset of these points are going to be the context for my denoising network. And then you will just apply your denoising network iteratively to denoise the query points given the context points, right? And again, you do this in reverse order, right? So this is the reverse process. This is really not that different from the standard formulation of a DDPM. And at the end, what you get is a function, continuous function F0, evaluated at the coordinates that you defined at the beginning, right? So, you can evaluate the same model. You can say, well, I want to sample a 32 by 32 image, or I want to sample a 64 by 64 image. And that's within the same network architecture. Cool. Are there any questions up to this point before I go into some of the results? I want to pause here to make sure that everyone is on board. Yeah, of course.
Isn't it the unit already incorporating context by the recipient?
Right. So the issue here is you cannot take a unit and apply it directly to a function, right? The unit has a very specific form. It needs to take W by H grid, right? Here is not taking a W by H grid, right? These are pairs of X, Y, RGB, and you can have a variable number of them, right? So that's a different, but yeah, look, the unit looks at context. It's just that you cannot take that network architecture and apply it to other domain.
Okay.
Yeah.
Yes,
Yeah. Yeah. Over there. Hi.
Why take the explicit route versus the?
Oh, absolutely. That's a great question. I sort of gloss over that. So in the implicit route, you have two separate training stages, right? The training stage in which you fit the MOPs to your training data, and the training stage where you train a generative model over the weights, right? The second training stage doesn't talk to the first one, right? The gradients are not backpropagated, right? So when you feed the MLPs, you don't really know about the task you're solving. That's a problem, right? If you go the explicit route, you can formulate everything in a single training stage. And that has conceptual benefits, but also empirical benefits, as I'll show in a little bit. Yeah.
So, like, also, I assume that then in the implicit route, you would be kind of taking the weights as the data, right?
That's right. Absolutely. Yes.
So there would probably be probably with the NLP having like the permutation and weighting, right?
Well, when the permutational invariance issue is not too big here because, well, the input to the MLP is the pixel coordinate, right? So you evaluate one pixel coordinate at a time, right? So it's not that you're evaluating sets of pixel coordinates together, right? So in a way, think about the MLP as just encoding the image, and you can sort of query it independently for each pixel. Yeah. Cool. All right. So here's some results. You can see here we have results on CelebiHQ, on CFAR, and also on ShapeNet. And these are three different domains. And let me stress here that we use the exact same network architecture for all the three data sets, right? So nothing changes. These are all functions, right? These are all well, not the same function, but these are all functions and can be parameterized as such. right? So that's a very interesting advantage to have if you want to leverage as much data as possible to train your generative model. So if you look at the FID numbers, you'll see that there's still quite a gap between domain-specific architectures and domain-agnostic architectures, right? So if you're going to train, again, using a convolutional network, you're going to get better performance, but obviously that's domain-specific as opposed to domain-agnostic. Yes, go ahead.
You're using the same architecture for sure, but are you using the same network? Are you training?
Oh, yes, yeah. So it's the same architecture. The only thing that changes is, you have different dimensionalities, right, for the different functions, but they all, like, implementation wise, what happens is coordinates go through this sort of like Fourier positional embedding layer, and you can make it so all of these outputs have the same dimensionality.
So for the 3D network, you just train the first layer, or are you training the whole thing?
You're training the whole thing from scratch.
Okay, so it's 3 different networks in the end, right? For the data.
Oh yeah, yes, absolutely. So it's the same network architecture, and it's one model for each. Yeah. So that's something that we're currently doing, though, training the same exact model. So it's like sort of like multi data set training. But yes, that's a really good point. It's one network with a different set of weights for Celibate HQ, for CFAR, and for ShapeNet. Yeah. Cool. So here's something really cool that I'm very happy to be chatting about, because we just put it up on archive a couple of weeks ago, and it's sort of like really a generalization of this idea of modeling generative models over functions and exploiting the generalizability that these sort of like architectures have. And the idea is the following. Like, we've talked about functions, right, whose domain were Euclidean spaces, like R2, R3 for video or for 3D geometry. But what happens really if you have a function that maps a curved surface to some signal space, right? And here, whenever you hear Riemannian manifolds, which is like a big mouthful, just think about a surface which is not flat globally, but is flat locally, right? So if you zoom in into a ball, right, you zoom in a lot, you're going to look at a plane and you're going to think, okay, locally this feels flat, but globally it's not really, right? So the technical way of describing this is that these surfaces are well approximated locally by an Euclidean metric, but globally they're not, right? And this is really interesting because we don't have architectures for this data. You cannot take a convolutional network and apply it to a curved surface. I mean, you can, but it's at your own risk. So this is really interesting because we can start thinking now about, well, what can we do in this case, right? So manifold diffusion fields is really a model that sort of sits in between diffusion probabilistic fields, right? So it's a generative model for continuous functions, but these functions don't live in Rn anymore. They live in some Riemannian manifold, right? And there's this area of Riemannian generative models that sort of like learn distributions over points that are living in some Riemannian manifolds, right? So here, A is what DPF does, right? So you learn a probabilistic model P theta of F over functions where, this particular function maps pixels to a Y space. And on the other spectrum, we have Riemannian generative models where you have points X that live on a manifold, like in this Stanford bunny here. So that would be the black points, and you learn a distribution over them. What manifold diffusion fields does is sort of in between, right? It learns distributions over functions where each function maps elements from a manifold to a single space. Right? And you may ask, wait, why, Miguel, why is this interesting at all? And the reason is that, a lot of scientific problems are defined on like functions on manifolds, like climate weather patterns, molecule generation, solving PDEs, and all that kind of stuff. Uses the machinery of Riemannian manifolds quite heavily. So the problem is the following: like, we knew how to encode a point, a coordinate on our end, right? So it's like if you have 2 dimensions, it's very easy to do that. But what do you do when you have a curved surface, right? Curved surfaces like the bunny here, the Stanford bunny, don't come with a coordinate system attached to them, right? So how do you define a coordinate? And the answer to that question is really simple. Is what you need to do is really, you don't need to define a coordinate system. The only thing you need to do is to find an analogy to the Fourier positional embedding that we use in Euclidean spaces. And it turns out that there's this whole field of spectral geometry analysis, which is focused almost exclusively on this problem. And you can take a thing that's called manifold harmonics. That is basically a generalization of Fourier positional embeddings to curved surfaces. And when they describe this, they're very technical and they like to mention Laplace-Beltrami operators and stuff. But the way to think about this is think about a set of axes on the bunny, right? And each axis is orthogonal to the previous axis, right? So there's a coordinate system. And this coordinate system sort of like, in a way, is a generalization of Fourier positional embeddings for Euclidean space. So using manifold harmonics, or in other words, in the paper, we call them the eigenfunctions of the Laplace-Beltrami operator. But using this, you can just plug these positional embeddings into DPF, and voila, you have a method to learn generative models of functions whose domain is Riemannian manifold, right? And it's actually a pretty effective way to learn this distribution. So let me show you a visual example so that it sort of like cements a little bit more what I mean. So here we have like MNIST digits, right? But these digits don't live in R2 anymore. They're not images. They live on some curved manifold, right? And so those are our training samples, and what I'm showing on the right is just the sampling path for a generated sample, right? So you wouldn't be able to do this with a convolutional neural network. I mean, you could say, well, this surface is almost flat, so I may get a reasonable result. But then I would say, well, I can make it even harder. And I'm going to take celeb AHQ images, and I'm just going to map them on the bunny. And then I'm going to use exactly the same network. And it is absolutely clear that if you take a convolutional network here and you try to do this, you're going to fail miserably. So, we have a bunch of other data sets in the paper. We looked at climate weather generative models and sort of like a Gaussian distributions on weird surfaces. We have the bunny surface, but we have a bunch of other manifolds as well. You can check the paper if you're interested. And of course, we have tables with boldface numbers because that's what you're supposed to have. But I think one interesting observation here is if you look at the paper, the difference in performance between MDF and DPF increases when the manifold gets more and more curved. And so that's what you would expect, right? If the surface is roughly planar, then you can approximate that with planar positional embeddings. But the moment that the surface starts to curve a lot, then you're missing out a lot of information if you don't parameterize your positional embeddings effectively. There's a couple more interesting things in the paper. This coordinate system this manifold harmonics thing that I mentioned is really interesting because it's also robust to rigid and isometric transformations of the manifold, which means if you have training data for a particular manifold like this cat here with that pose, and you then test it on a rigid transformation of that manifold, or even on an isometric transformation and a reposing on the manifold, the model generalizes automatically to that case, just because the coordinate system that you're using is intrinsic to the surface. So I'm almost done, but I wanted to show you some additional results of temporal functions on manifolds. So these are videos you can think of as videos. And what we did here is we just take the Stanford bunny, and then we simulate a bunch of solutions to the heat diffusion PD. So, you start with a heat source on the bunny that's encoded in red, right? And over time, the heat diffuses, right? And the whole thing sort of like comes to an equilibrium state, right? So you can simulate a bunch of the solutions to that PDE given different initial conditions, and you can use that as training data for the generative model. Right, and you can see that the samples that you generate are distributionally really similar to your training data. So that's really interesting because then what you can do is you can apply this sort of probabilistic model to solve PDEs both in the forward and also in the inverse way, right? So you're given some initial conditions, right? So A here is the classical solution to the PDE. B is a solution that I like to call sort of like a probabilistic solution because it's stochastically sampled from the model. So the model observes the initial condition that predicts what's a likely rollout of the system. But also you can use it to sort of fill in. So you have sparse observations of the system. So you have the bunny here and you observe different pixels at different time steps, and you can ask the model to fill in, much as you have seen generative models filling in images. Cool. So that's pretty much it. I think, I hope that could translate a little bit my enthusiasm about this sort of like functional parameterization of data. I think we're just barely scratching the surface. I think about these two works as sort of like almost a proof of concept that this is doable, right? But now the real question is, well, what happens at scale, right? You want to train this on lots of different data sets, lots of different domains at very high resolution, how we do that, right? I think implicit and explicit functional parameterization matters a lot, and there's a question there. For that, I think that's really a key question. If you can formulate everything into a single training stage, you get a lot of benefit out of it. And with this generalization of functions to manifolds, we can sort of attack a lot of problems in the scientific domain. So something that we're looking into right now is generating molecule conformers, which is basically a generative modeling problem over graphs, which is what a manifold really is. So you get a lot of things you can do if you follow this path. So if you're interested in collaborating, or if any of this looks interesting and you're looking for internships or full-time positions, whatever it is, please feel free to email me, and I will love to answer some of your questions. Thank you so much. Yeah.
Thank you for the presentation. So I'm thinking like about the route. So I have two questions about it.
Yeah.
First, there are but many MLPs that we exactly the same, that we be able to represent exactly the same thing, right? Just because of the fermentation of the way to look. My first question would be like, how would you try to manage that? Like, it doesn't matter. For me, it doesn't matter.
That's a really good question. Stochastic gradient descent is indeed stochastic, right? So when you're trying to optimize for the weights here, if you make two runs, you're going to get a different set of weights. That's a problem conceptually, I think, for this kind of approach. I think in practice, they don't observe that kind of issue. But again, it might be an issue if you try to train this at scale. I think one of the issues also of this implicit route is that if you try to scale up this architecture, excuse me, let's pretend for a second that you have a data set of 10 million images, or whatever, 400 billion, whatever it is, the biggest data set that you can think of. Then you need to train an MLP for each sample in your data set. But that's not the problem. The problem is that every SGD update is local to just one sample. Right? So you're not using the same SGD update to update all the other MLPs in your network, right? And that's a huge problem for scalability, because if you're given a budget of, have 10,000 SGD updates, then the ratio of SGD update per sample goes down as you increase the number of samples. That's a really terrible position to be in if you think about scaling up this architecture. So I think there's definitely theoretical issues with it, but there's also very strong practical reasons why you would want to go the explicit route versus the implicit one. Yeah.
Question is, so for instance, if you were trying to generalize this to NERD. Right?
Yeah.
An image is just an image, right?
Yeah.
The NERD is learning a field which then has to be rendered.
Yeah.
So there is this coupling between what the NERD is, but then through the rendering equation to volumetric rendering, you actually get the image. Does like would introducing this into the pipeline make sense? That being difficult?
Yeah, I mean, that's a really good question. So I've worked on generative models for nerves before, so I'm like fairly familiar with the approach. I think in the case of nerve, it's tricky because nerve is not only a representation, is what you said. It's not only just a field representation, it's the operator that you use to compute images to get supervision. If I were to think about how to use this kind of approach for 3D, I would probably not go the nerve route. So there's other ways of thinking about 3D renderable data structures. One that I think has a lot of promise is a light field, which has its own issues, but you don't have the rendering issue. So I think that's a really promising direction. I will say just that.
Yeah, because of time,
Oh.
we need to thank now Miguel Angel. Thank you again.
Thank you so much.
And the next session is the poster session. So I invite you all to take your posters and place them.
Hola Luis, ¿escucha?
Hola, sí, ¿qué tal?
¿Cómo estás? ¿Todo bien? Estamos
Bien,
aquí
bien, ¿tú qué
ahora,
tal?
ahora todo el grupo está en el poster session,
Ah,
entonces
excelente.
ya lo que vamos a hacer es probar, ¿sabes? Que todo esté bien y ya a las 3:50 empezaría el tutorial, entonces como a las 3:40 te unes de nuevo para...
3:40, ok, sí, hola, ¿cómo vas? 3:40 es en una hora, ¿cierto?
Ajá, en una hora. Pero para
Ok,
chequear que todo está bien y ya, entonces ahora yo voy
entonces
para el poster session.
espérate, hago mi share screen. ¿Puedo hacer share screen?
¿Y qué?
Compartir mi pantalla.
Ajá. Hi. So we are in poster session now, and we're back at 3:50. Yeah, yeah.
¿Ves lo que está pasando,
Nice. Yeah,
cierto? ¿Veslo?
yeah. They are like sponsor here. Yeah, but everyone now is going to the poster session, so like everyone is there. That they will come back 3:50, and then we have like a tutorial and then like closing remarks. Yeah, thank you.
Tú ves las pantallas moviéndose, ¿cierto?
Sí, se ve perfecto. Ajá, perfecto.
Ah,
Yeah.
bueno, excelente. Entonces, pues así quedamos. En una hora me vuelvo a meter. ¿Listo?
Un momentico. Yes. So poster section is from like when you go to like all the way to the end, like go down, and there is like a lot of posters there, like but there are many. So then our session is from poster 200 to 300, like 234. All these, yeah. Thank you. Yeah,
Listo.
so, perfecto. Entonces a las 3, ahora voy
Cualquier
para el poster
cosa me
session.
escribes por teléfono, ¿listo?
Igual, y ahí entonces ya cuando vayamos regresando te envío un mensaje y entonces a las
Bueno.
3:40 yo me conecto de nuevo y ya lo que probamos es que esté todo
3:40.
bien. Ya empieza el tutorial a las 3:50.
Y tengo una hora, ¿cierto?
Tienes una hora, puedes usarlo, ¿sabes? Prepararla ahí como te sea mejor y dejas un tiempo al final para las preguntas. Y después, si quieres, nos compartes cualquier información para compartirla con todos los muchachos. Y nosotros hay las preguntas que estén, sí, la mayoría del grupo está aquí. Vinieron casi 50 personas, un grupo bien grande. Entonces ya todas las preguntas que dan aquí te las compartimos. Y bueno, si hay preguntas en el chat también la chequeamos y bueno, ya lo ponemos, lo ponemos ahí en el Zoom en el chat.
Buenísimo.
Perfecto. ¿Y cómo
Excelente,
estás?
listo, bueno.
Bien,
Bien.
todo allá?
Bien.
Bastante trabajo.
Sí, bastante. Un poquito ocupado, pero todo bien. Sí, la conferencia bien, todo.
Todo bien, sí,
harta gente, ¿no?
sí, ha estado bastante bien, bastantes presentaciones, las presentaciones han estado bien buenas. Y ya, por la mañana fueron 2 keynotes y las presentaciones, y ya después paramos el lunch, después el lunch, Miguel Ángel acabó de hacer la presentación, ahora hizo como la parte de research de Generative AI. Está bueno porque entonces ya como que dio un background en research, entonces ahora con lo que explica yo creo que ayuda también a ¿sabes? Como que, porque fue más research, ¿no? Ahora es como que más tutorial porque hay personas que no
buenísimo.
saben.
Pues yo tengo un GitHub link, entonces les puedo dar el link si el que quiera irse metiendo y pues yo muestro más o menos el lab. Es un lab bastante sencillo. En realidad tengo la charla es media hora y el lab pues también unos 10 minutos, pues si quieren preguntas o algo, pues.
Perfecto. Ya, entonces lo que podemos hacer es compartimos dar la charla y si quieres comparte el link de GitHub, ya yo lo comparto en el grupo y ya cuando empieza la charla ellos pueden ir accediendo al Git de GitHub y ya cuando empieces el lab ellos pueden ir contigo siguiendo en el
Te lo mando
lab.
ya mismo.
Perfecto.
Te lo mando por acá.
Sí, por acá está bien. Yo lo comparto con... Perfecto. Entonces, lo que les digo es que usen ese link para la parte del lab, ¿no? Va a tener una charla en la parte del lab que ellos lo sigan por ahí. Perfecto. Les deja un tiempo para que ellos hagan preguntas y bueno, es más bien, ¿sabes? Para que la persona... tranquilo.
Yo lo hago con calma. Es una charla de media hora, pero si la hago como con calmita, 40 minutos y después en la... Está bien. Bueno, excelente.
Perfecto.
Bueno, entonces hablamos contigo. Bueno, no, tiene la invitación. Bueno.
En cuanto estés regresando, les envío un mensaje y en una hora más o menos nos volvemos a reunir.
Listo, una hora está acá. Bueno.
Perfecto. Muchísimas
Gracias.
gracias.
Chao, chao.
Nos
A
vemos
ti.
en un
Chao.
ratito. Chao, chao. Chao.